Okay, then good morning, everyone. Then we are going on our next day. Then we learn about the atmosphere, we learn about the land and the sea ice, and today we will have 3 talks related to the ocean. Then first, a few logistics for the day. Then we have our second session of Meet a Scientist. Then you are over there with the assignment. I think also you send them an email if you don't have this. Then try, if you are meeting a scientist, try to leave at noon from the library to get your lunch, and you are welcome to bring your lunch in the room. It's the idea. It's that you have lunch together with the scientist and a very small group of people. And if you are not meeting a scientist today, wait a little bit, 5 minutes or 10 minutes before going to lunch. Then today in the lab, we are going to say, in the rough guideline, to say day 3, it's the name list, troubleshooting, and when you do source modification to the code. But once again, it's a self-paced lab. You are welcome to move at your own pace. Then if you haven't finished exercise, you can go. If you are going faster, you can move forward. There are a lot of exercise today. And the last thing is that if you are having trouble with the tutorial queue, we have the instruction how to use the tutorial queue. If you are still having trouble, please let us know. The instructions are here. The tutorial queue you use only during the lab, otherwise you have to use the main queue. Okay, any question? Okay, then we will go to our first speaker, Gustavo. And if somebody asks a question during your talk, usually they wait, but if there were clarification, repeat the question because it's recorded.
Okay.
Thank you.
Good morning, everybody. I'm Gustavo Marquez. I'm with the Oceanography section here from NCAR and CGD. I've been the Ocean Model Science Liaison for CSM since 2017. And then in the beginning of this year, I became a co-chair of the Ocean Model Working Group. So I'll talk about ocean modeling basics and give you an overview of the ocean models that we have in CSM. But before I start, I have 2 questions. So I hope these 2 questions will convince you that this is the most important component of the climate system. The first question is, well, I'll let you decide after you answer the 2 questions. The first question is, does anybody know what percentage of the heat, the extra heat that has been released into the atmosphere since the pre-industrial era has been absorbed by the oceans?
More than 90.
You guys are very good. 93%, that's the best estimate. And what percentage of the CO2 that has been released since the same time has gone into the ocean? Anybody? Oh.
Half-ish?
No, 0.25%. So half is in the atmosphere, 1/4 in the ocean, and 1/4 by the land model, in the land. Therefore, no, the ocean has been absorbing most of the heat and has been a key contributor in absorbing the CO2. So the climate is what it is now because of the ocean. If it was not for the oceans, it would have been way worse than it is right now. So every morning from now on, we all, before we check your phone, you should say a prayer to the oceans, thanking for making its role. And we should do our role as well in helping minimize climate change. So I hope I've convinced you that this is the most important component. Okay, so overview of what I will talk about today. I'll give you a general sense of what are the principal model considerations we should have when doing ocean modeling, the challenges, some of the ocean properties. Then I'll go through the governing equations in the models that we use, the boundary conditions, and the horizontal and vertical discretizations. Then I will introduce the two models that we are using right now. So the first one is Parallel Ocean Model version 2, or POP2. So this is still the model that you guys will be using in most of the simulations. So this is the supported component in CSM 1 and 2. Starting CSM 3, MOM6 will take over. That will be the only component available. We will drop POP2. So right now, some of the CSM sandbox have both, and where MOM is an optional component. And we do have a few exercises with MOM for those of you that would like to get going with it this year. But no, next year, this lecture will not include POP and as part of it. And then finally, I'll end with some helpful resources. So the first order challenge in terms of ocean modeling is the irregular domain that we have in the ocean and the land-ocean boundaries. So I'll show you an animation. This was done by the MIT groups using MIT GCM, a different ocean model, but it's a very illustrative animation just to help us see how the land exerts important control on the ocean currents. So let me... All right, so now we're kind of in the North Atlantic. We're going towards the coast of the United States. So you see the Gulf Stream. Pay attention how the current is being dictated by this channel between the south of Florida and Cuba, these eddies in the Gulf of Mexico. Like now between Cuba and Central America, you also have this little channel, the Yucatan Channel, where the flow needs to narrow down and becomes very strong. We are moving towards the equator. Now you see these eddies being shattered by the North Brazil current. In the equator, the currents mainly follow the trade winds. Now we are in the southern tip of Africa. These are the so-called Agulhas rings. Look how they are formed between Africa and Madagascar. So now again, that's the land exerting a control in the flow. The flow separates, go north and south. Anyway, now we are going towards the Indian Ocean. I will not go to the whole movie, but just to give you a sense how the irregular domain is dictating how the ocean currents look like. So this is the first order. Like it's very unlike in the atmosphere where the mountains have a control at the bottom, but there's not much horizontal constraint in the flow. In the ocean, is not the case. And we are looking at the surface. As you go down the water column, sea mountains become exert an influence too. So if you have the same animation but at a different vertical level in the ocean, you see a different picture. All right, now moving to the horizontal and spatial scales in the ocean. So this plot showing the x-axis are the spatial scales going from 1 millimeter on the left to 10,000 kilometers on the right. And the y-axis are the time scales going from 0.1 seconds to 10,000 years. So on the very left, bottom left, you have things like molecular processes, capillary waves, and on the far right, you will have climate change, El Nino, so very large and slow processes. If we use the coarsest resolution ocean model that we have in CSM at the moment, which is a 3-degree horizontal resolution, so this is what we use for paleo applications, BGC, like really long integrations. That's the green box represented there. Those are the processes that we will be capturing with the low resolution model that we have. So basically, we can do these very slow and large processes. We can represent them. Similarly, if we use the workhorse 1-degree resolution, which is the model you guys will be using in the practical, is slightly better. Like we can now do a little bit of eddies and fronts, mostly at low latitudes. But still, like we're capturing like these large, small, large and slow processes. Now, this is the highest resolution configuration we have in CSM, is a 1/10 of a degree, or 0.1 degree. That's the red box. Now we're kind of representing most of the eddies, still not the whole mesoscale field, just a significant more than the 1 degree, but still not everywhere. I'll show you in a second. But it's, it's still like we are not getting, like we're getting most of the slow and large, but not the fast and small processes that we have represented in this graph. So the bottom line is most of the global ocean models simulate the climate. If we do an analogy with the atmosphere, again, the same type of plot and the processes occurring in the atmosphere. And now the black box, this is the workhorse 1 degree atmospheric model, same the one that you guys are using. Now we are capturing these processes. So notice that the eddies are, most of the tropical cyclones are being captured by 1 degree atmospheric resolution. Therefore, what we say is that most global atmospheric models simulate the weather. It's this similar resolution in both, but in the atmosphere, you can capture way more of the mesoscale field, while in the ocean, you cannot. So that's a big difference. Like one, we are capturing climate, the other one, we are capturing weather. And it will be, I'll show you in a second why that's the case. All right, the bottom line for in ocean modeling is, so these two snapshots shows sea surface temperature at a particular day. On the left is with a 1/10 degree resolution ocean model. And this is just the southern tip of Africa. So you're looking at those Agulhas rings that we saw in the animation. So you can see some of the rings. Is this working? Point. Oh, nice. Yeah, so we can see the rings here being resolved-ish, like you can identify them, you see these blobs. On the right, on the other hand, this is a 1 degree model, so it's very smooth, like we don't see those same eddies. The bottom line is when we use these 1 degree models, low resolution models, we need to parameterize or come up with ways of using the large scale field to represent the effect of these small scale features in the tracers, momentum equations, as well as in the energetics. So a lot of the business that we do in ocean modeling, global ocean modeling, is come up with parameterizations. The next ocean lecture that Peter Jen will give, he will talk about some of these, in particular the mesoscale parameterizations that we use in these models. Now, why is the Rossby radius of deformation, or let me step back. Why do we need high resolution in the ocean models compared to the atmospheric models? One parameter that we can use to assess how well the model represents the mesoscale field is the so-called Rossby radius of deformation. And it's given by these equations, so it's the ambient stratification n times vertical scale, capital H, divided by the Coriolis parameter, and we have pi as well in the denominator. So that's what we use. And in the atmosphere, the density difference between, let's say, the top of the troposphere and the surface is much larger than the density difference between the surface of the ocean and the bottom of the ocean. Therefore, the Rossby radius of deformation is much larger in the atmosphere compared to the ocean. So in the ocean, it ranges from hundreds to tens of kilometers, while in the atmosphere, it ranges from hundreds to thousands of kilometers, so an order of magnitude larger. So that's why we can use the 1 degree model represents way more processes in the atmosphere compared to the ocean, or like I should say mesoscale, or weather-like. So this map shows so this is the ratio between the Rossby radius of deformation and 2 times grid space delta x given by in degrees. So the grid space here is given in degrees. So if you look at the light purple on the far left of the color bar, that's where like the equator gets highlighted, right? So with a 1 or half of degree ocean model, you will be able to represent the baroclinic radius deformation in the equatorial region. That's it. If we want to resolve in most places, we need to go to the far right of the color bar. So that's like 1/25th to 1/50th of a degree. So that's where you can capture most of it. So that's very high resolution ocean model. Also, like we're saying that this study is making the point that you need 2 grid points to represent, at least 2 grid points to represent the ranges of deformation. It's still debatable. Some people argue that you need 4, at least 4. So if you assume 4, then this is going to get even more expensive. Another challenge that we have is that processes in the ocean tend to be adiabatic. So there is little work that happens once the water mass is sinking. So this illustration is after Ferrari et al. So this is kind of a conceptual model of how mesoscale eddy fluxes occur in the ocean. So in the ocean interior, here, so the gray lines represent isopycnal, so line of constant density. So in the interior, these isopycnals seem to be tilted. And in the interior, the mixing occurs mostly along isopycnals. You have very little mixing across them. These red lines, these red arrows are very small compared to the blue arrows. And as you approach a boundary, it can be the surface, can be the bottom, the fluxes tend to then be along the boundary. In this case, they are lateral or horizontal, right? Here. So now you can have fluxes across isopycnal. So the blue arrows are crossing the gray lines. You also have vertical mixing too, because you're near the ocean, you have convection, you have all the wind and the surface, the heat fluxes and the buoyancy fluxes in general. So it's a distinct regime. Like in the interior, the flows tend to be what we call adiabatic. There's very little work, and things mix along isopycnal. And as you approach boundaries, such as the surface, things get way more chaotic and mixing happening in all directions, including across isopycnal. So to represent the interior mixing in an ocean model is very, very challenging. Imagine if you have like discretization errors, errors related to your advection scheme, any extra mixing that the ocean model puts in the interior will deteriorate your solution because now you're breaking this adiabatic assumption. So a lot of the things that we do is try to minimize spurious mixing in the ocean interior. Because there's very little mixing when the water masses sink, that's why we can name the water masses. So you have many different names: Antarctica bottom water, Antarctica circumpolar deep water, North Atlantic deep water, and so on and so forth, as shown on the bottom right. And so this is a consequence of the little mixing that occurs once the water masses are buried. Okay, so this is what I just said. There's very little mixing in the ocean interior, and that's why the water can be named. And we can now use mixing arguments to infer how long it will take for the deep ocean to be in an adjustment state. And to do that, we can say, okay, let's get a typical depth of the ocean, let's say 4,000 meters, so that's capital H, 4,000 meters squared, and divide by a vertical diffusivity, can be molecular vertical diffusivity, let's say 2 times 10 to the minus 5 meters squared per second, and that gives you 20,000 years. So that's how long it will take for the ocean interior to achieve a quasi-equilibrium state. It's a very long time. We can also use dynamical scaling to come up with a time. And for that, we can use, for example, the phase speed of non-dispersive Rossby waves, which is given by this expression, C sub r. And we can take values from, let's say, the Pacific Ocean, so the width of the basin, and then the times that it takes for this wave, the phase speed of these waves, and then divide the length scale by the velocity of these waves, and then you get approximately 2 years, so much faster than the other one. But again, we are limited by the other adjustment due to mixing, which is very, very slow. So the bottom line is, for climate studies, like all the climate studies, especially at high resolution that you work with, eddy permitting or eddy resolving, which are now becoming more common, they will not be at equilibrium. The ocean will not be equilibrium at depth. So we must live with that. And also, I mentioned the spurious mixing in the interior. Even though we tried the best to minimize them, there is always some spurious mixing. And you have to keep that in mind as well. Like when you, especially the long integrations, some of the ocean interior, the water masses will be modified unintentionally because of spurious mixing. Again, it's getting less and less now because of some of the vertical coordinates that we are using, which I will get in a second. I did not mention this, but no, I asked the question about, I convinced you why the ocean is the most important component, and one of the reason is, or one of the reasons is the heat capacity of the ocean is much larger than in the atmosphere. And this makes the ocean an important heat reservoir. And that has implications for long-term predictions. So we always say the ocean has the memory of the climate system. So more and more researchers are looking into ways of finding answers about the future by looking at the ocean state. Okay, so I covered the first part of the lecture. Now we'll get into the equations that are used to solve ocean models. I will go very quick. I know this is kind of a general overview. Don't bother about the details. Like, please come talk to me if you have other questions, or there's plenty of materials online. So if you're not familiar with equations, if you get caught up by the math, don't worry. Just try to listen the main message. So we have 7 equations and 7 unknowns. That's how we solve things. So these equations are these 3 equations for the velocity components, u, v, and the vertical. There's an equation for temperature. There's an equation for density. There's an equation for pressure, and there's an equation for salinity. Plus, if you're doing biogeochemistry studies, or if you have some kind of a passive tracer, then you need an extra tracer equation for each of these tracers. For example, CFC's ideal age. And we perform some approximations into these equations so we can simplify the terms. And the first approximation is the so-called hydrostatic approximation. So in simple terms, hydrostatic approximation is we cannot allow for overturning in the ocean. So if you're familiar with like Kelvin-Helmholtz instability, like these really strong stabilities that happen, we can see them in the clouds sometimes. They do not happen in the ocean models that we use for climate studies. And that boils down to like all the vertical accelerations larger than gravity are neglected. So instead, like when we are resolving the equations and we compute stability, we see that there is a dense water above lighter water, so it's unstable. We just crank the vertical diffusivity and viscosity very, very large. So instead of, like in nature, you would mix by these Kelvin-Helmholtz processes, but in the ocean model, we just say, there's very large mixing happening here, just mix these things really quick. And that's how we do. The other approximation is the so-called Boussinesq approximation. So in this approximation, we say that the density in the ocean can be represented by a mean density, rho naught, plus a perturbed density, rho prime, where rho naught is much larger than rho prime. That's a very good approximation. So by doing that, we neglect, in the equation of motions, we neglect rho. We use rho naught in most places except in the hydrostatic equation. So we substitute rho by rho naught in most places. Nowadays, some ocean models are running non-Boussinesq. The main advantage of doing non-Boussinesq is for sea level rise studies. And I won't get into the details, but MOM6, for example, is one ocean model that can be run on with both Boussinesq and non-Boussinesq approximation. Okay, moving on. The third one is the continuity, or the incompressible form. So we cannot deform the seawater, meaning that if you have a control volume, if something comes into one side, a volume comes in on one side, the same amount must come out somewhere. Then we have the thin shell approximation. So the best way to represent the dimensions of an ocean is with the thin of a sheet of a paper. That's it. So these are horizontal versus vertical scale in the ocean. The vertical scale is much smaller compared to the horizontal. Therefore, what that implies is that horizontal motions tend to be much larger than vertical motions. So this is a so-called traditional approximation. And the thin cell approximation has a lot of implications for simplifying the equations of motions. For example, you can simplify the Coriolis parameter in the horizontal components, U and V. Sorry, you can remove the horizontal parameter only come in the U and V. You can neglect in the vertical direction. Moving on, we have this spherical Earth approximation. So the geopotential surfaces can be assumed to be the sphere. And then finally, we have this, we use what we call turbulent closures. So because we look, the horizontal and vertical grid spacing ocean models are small, or sorry, are large compared to the horizontal and grid scales are large and can now represent most of the processes, the turbulent processes. We need to come up with these parameterizations that I mentioned before. So therefore, like the ocean models used in climate simulations are full of turbulent closures. And Peter Jen will talk about a few of those in the follow lecture. Okay, so now moving to the equations. So these are the Boussinesq hydrostatic equations in high coordinates, in Cartesian form. So first we have the horizontal momentum, then you have vertical momentum, hydrostatic equation, then mass and continuity equation, mass conservation and continuity equation. Now an equation for temperature transport, similarly for salinity transport. If you have another tracer like CFCs, it would be a similar equation to these two. Then you have an equation for equation of state, which is nonlinear. It's being simplified here, but no, that's a very complicated and large equation as a function of temperature, salinity, and pressure. Okay, and that's it. So we've covered the equations and the variables at play. Again, just a big picture overview. Now let's talk about the boundary conditions. So starting with the surface. So there is at the surface of the ocean, we exchange fluxes with other components, atmosphere, sea ice, and these fluxes are related to momentum and tracers. In POP, for example, we do not exchange fresh water. Instead, we use the so-called virtual salt flux. So if it rains on top of the ocean model when you guys are running with POP, instead of throwing fresh water on the top of that ocean cell, we say what would be the equivalent in removing salt, or if it's precipitation, or adding salt if it's evaporation, that would result in this water having the same properties. So that's what POP does. MOM uses actually fresh water, is a natural boundary condition model. Okay, now moving to the bottom of the ocean. So there's no tracers flux through the bottom of the ocean, except in MOM6, we have the option to apply geothermal heating. So you have certain places in the ocean where you have these thermal vents that are releasing heat into the ocean, and we have the option to represent that in the new ocean model MOM6. That is not available with POP. We have a normal velocity. The normal velocity at the bottom is 0, and we often assume a quadratic bottom friction at the bottom as well. In terms of the lateral boundaries, there is no tracer fluxes at the lateral boundaries, and there's also no flow normal to these boundaries. So it's a solid boundary condition. Meaning, and we also apply a no slip. So there's always a friction when you exchange momentum right with adjacent to a land cell, for example. Okay, now moving to the horizontal grid staggering in these models, again, covering only the cases that we use in MOM and POP. So starting with POP. So POP uses the so-called Arakawa big grid. In the Arakawa big grid, so this is a representation of an ocean cell. And in the middle, you have tracer points. So temperature, salinity, CFC, all your BGC tracers are represented at the middle. And then the corners, the four corners, you have U and V both happening there. So U and V are the same point, and tracer is in a different point. Tracers are in a different point. So there's many advantages of using a Arakawa big grid, especially at low resolution. So it naturally fits the no slip boundary condition that I mentioned before. You have better dispersion relation for Rossby waves at coarse resolution compared to C-grid, for example. And there's also smaller truncation errors in the Coriolis term, in the discretization of the Coriolis term. So these are some of the advantages of a big grid. However, there are major disadvantages. And I'm mentioning here one, which is because your U and V are on the corner points, if you have, let's say this schematic, you have land points in green and ocean points in blue, and you have a channel that the water needs to flow through. If you have only one ocean cell here, instead of two as shown, you cannot have flow going through that channel. You need at least 2 grid points between land points in order to have the flow going through, because the velocity is at the corners. So this has major implications. I showed you that animation earlier of the irregularities of the oceans, and we see a lot of little channels. So when we are using a big grid, you need to ensure that every channel has at least 2 grid points. Otherwise, the flow is not going to go through. So again, this is the staggering grid used in POP. Now moving to Arakawa C grid. In this case, the tracers are in the center, and then U points are on the same level as the tracer, but on the left and right faces. So these are U points. Oops, it's really hard to. Oh. And then V points are on the bottom and top faces. So here are the V points. So they're not all at the same location. So tracers U and V are different locations. That's the main thing. And this allows for a single point channels. Because now, if you have only one point, you have at least either the U velocity or the V velocity is being represented. However, it has disadvantages, so it's basically the opposite of the other one. The Coriolis acceleration terms require horizontal averaging, and that makes, it leads to less accuracy in the representation of the Coriolis force, and also has worse dispersion relation for the Rossby waves at coarse resolution. And this is what we use in MOM6. Okay, now moving to the vertical coordinates using ocean models. In conjunction with the horizontal resolution, the next most important aspect is the vertical choice of coordinate and vertical resolution. And this is very, very important. And there's currently 3 main vertical coordinate systems in use in models. The one on the left is the so-called geopotential coordinate, or Z coordinate. That's the one that's used in POP. So you have the distance between 2 lines here is the delta Z. That's your vertical resolution. You tend to get smaller delta Z's near the surface and larger delta Z's at depth. And it's the same delta Z horizontally. You cannot change your delta Z as a function of horizontal position. So if you have a delta Z of 500 meters here, it will be 500 meters in the equator. It will be 500 meters at high latitudes. The second coordinate in the middle is the so-called sigma, or terrain falling coordinate. In this case, your coordinate is following the topography. So look how it follows the bottom of the ocean. It's a very good coordinate for coastal regions, because you can get good representation of the bottom processes as well as the processes near the surface. And then the one on the far right is the so-called isopycnal, or density-based coordinates. So now look how your delta Z's are changing as a function of the position. So you have a small delta Z here, here, and a very large delta Z in the interior. The main advantage of the isopycnal coordinates is because I mentioned earlier, there's very little mixing when the water masses are buried, and they tend to mix along isopycnal. So that is a natural coordinate for representing ocean interior processes. So all of these have their advantages and disadvantages, And lately, what we're trying to do is create these hybrid coordinates. Okay, I'm running out of time, so I'll speed up. Hybrid coordinates where we combine two or more of them into a single coordinate. That's an area of very active research and development. If you are interested in working on this, please come talk to us. We need people working on this type of problems. All right, so just to show MOM6, we'll be moving to a hybrid coordinate with MOM6. That will be the out of the box starting next year. You have Z star near the surface and density at depth. This is an example of a Z star coordinate in MOM, and on the right are the Z star coordinates in POP. Okay, so there is when you can run ocean models with fully coupled B cases, which you'll be doing the exercise, but you can also run force cases, either C comp sets where all the forcing is provided via data. We rarely run C comp sets. More often we run G comp sets rather, which are sea ice and ocean are active. And there is an exercise to run a G comp set in the Jupyter book if you're interested. And then for the forcing, there's different options you can use. The so-called core forcing, which is a little outdated now. We've been using the GRA 55 forcing, which stopped last year, 2023. End of this year, there is an effort that will come up with a new forcing protocol that will be the next one to be used. Okay, really quick about POP. So it's a Z-level coordinate, hydrostatic, Boussinesq. It has some implications in the linearization in its formulation for the implicit free surface used for baroclinic and barotropic pressures. And I mentioned already the virtual salt flux. It does not use the natural boundary condition. We have a few options for grids using POP. The displaced pole, so this is the one that you guys will be using, the GX1. So the pole here is being moved to on top of Greenland, and has two poles, one there, and the other one is the southern pole. So the GX1 and GX3, which is the nominal 3-degree, use the approach, and we also have a tripolar option for the high resolution 10th of degree. So now we have three poles, one in North America, one in Russia, and then the one in Antarctica. MOM is a finite volume solver, can do hydrostatic, Boussinesq, and non-Boussinesq. And I mentioned the non-Boussinesq for sea level rise. The big change here is that MOM6 uses an arbitrary Lagrangian Euler approach for the vertical coordinate. That means we can represent any combination or any coordinate or any vertical coordinate or combination of them together. An example here of different coordinates used to represent a overflow. It has many other built-in things that like subcycle of gravity waves, built-in wet and dry. Is a huge list of the submesoscale closures. So this is what we call open development ocean model. Like anyone can contribute to MOM6. Therefore, the list of parameterizations are very vast, and it keeps growing every year. We need to, at some point, we'll have to use 2 pages. I'm just simplifying some of them here. I'm going to go really quick. So we represent ice shelf ocean interactions in MOM6 because of this built-in wet and dry. So in this case, we have the ocean melting this ice sheet, and then the grounding line, which is highlighted by the arrow, is moving as it does so. So this is a very difficult process to represent in an ocean model, and MOM6 does it really well. And then just really quick, so this is in the exercise. So you can now run MOM6 as an optional component, but you can run, and I'm putting the link here to the exercise for the afternoon, for the later session, the practical session. So if you're interested, you can follow these steps and run a GKs with MOM6. We are supporting, we have tripolar grids being used in MOM, and this is the TX23, is a nominal 2/3 of a degree, is a weird number, but yeah, it's 0.666 of a degree. So that's the one that we have that you can use today. And we've been doing we've done more than 100 fully coupled simulations as part of the development for CSM3. Cecile is the person doing them. She is the expert in doing fully coupled simulation. She has probably 10 simulations going on right now. So, and it's just to mention, is doing as of now, we have similar biases that look showing SST biases. The biases are similar to what we get with typical climate models, as good, if not better, than what we get with POP. Okay, we can do other type of studies with MOM, like idealized, aqua, and rigid planets. And also we have this high resolution option to do with MOM is a 1/10. We are developing a 112 at the moment. And another advantage of MOM, you can do regional simulations. So we have two examples here for one in the East Pacific, and the other one is in the Caribbean and Gulf of Mexico, led by students and researchers here from NCAR. So we can do like actionable science with these regional high resolution applications that are not possible with MOM6. Okay, so hopeful resources here for POP. There's a lot of material online, and there's also the forum for asking questions. But remember, POP is going to be abandoned in the next release of CSM, and also here for MOM6, there's a lot of resources online, including diagnostic packages, tutorials, webinars, and also if you have questions, there's the CSM forum for MOM6. Feel free to reach out. We are always available for answering questions and engaging into research opportunities. These are the references, and please subscribe to the Ocean Model Working Group if you're interested in becoming part of it. Here's my email. I'm happy to take any questions. Thank you.
Yes, thank you so much. We have a few minutes for question, but I will ask you to stick during the break if you can,
Sure.
if there are more questions. Then question for Gustavo?
Hi, thank you for the talk. I realized, I guess, like you were talking about the boundary conditions of the ocean model and spoke about the surface boundary conditions. And I noticed you mentioned that there was a momentum flux, but you didn't mention a heat flux. Is there a reason that there isn't a heat flux?
No, there is.
Oh,
so there's
there is,
momentum
okay.
and buoyancy, and in buoyancy you have both heat and fresh water.
Okay,
Yeah.
sounds good. Thank you.
Yeah, you're welcome.
I was wondering if you could speak a little bit more about the mixed coordinate systems. So you said you could represent them using z or sigma or isopiconal coordinates. When you actually run the model, is it using one of those, or does it choose which one to use depending on where you are in the ocean? How does that work when you're actually running the model?
You need to tell the model which formulation you want to use. And right now, like the bottom left, here's an example of a hybrid. So there's two vertical coordinates being used here. So you see in a really high resolution, this black line near the surface. So this is a Z coordinate, geopotential height. And then as you go in the interior, now they become more apart from each other. So that's a density based. And notice that you have a pretty large gap here. That's because is not stratified. It's like well mixed, and then the density coordinate became a kind of is not doing a great job because you're not like you have important processes happening there that are not being represented. So this kind of boils to ocean model development rather than like the user. Once you start running, you don't have control of these like. And so we, as model developers, we try to come up with an option that will represent the process at interest as much as possible. So it's kind of an art, and we are learning like this. That's why I mentioned this is a very active area of research with opportunities for improving the model. So yeah, answering your question is kind of, as the user, you choose one. You say, I want hybrid, and I specified, this condition for transition from a Z star to a density is just like when you provide your densities, you tend to provide a lot of light densities as well, so that you force the model to be Z star, because the model is going to go and say, the density here is 1030, but my first option in the density coordinate is 1000. So therefore, I go to Z star. And it keeps doing that until it finds a density that is existent in your density coordinate. So yeah, it's complicated. I can talk more about it, but I hope I gave you an idea.
Thank you.
Hi there. Thank you.
You're welcome.
I wondered about how you initialize the deep ocean and how you handle that problem, or maybe not problem, I don't know, to not be in equilibrium in deep ocean. Do you have some tricks to get close? Do you just make up your deep ocean, or do you have observations you rely on?
Yeah, so we typically initialize from the World Ocean Atlas, temperature, the tracer's temperature and salinity, and it starts at rest. So when we do pre-industrial control simulations, that's how we start, and then we integrate for very long in the pre-industrial mode, and then we transition to a historical. So there will be drifts that need to be accounted for. So that's kind of how we've been doing. To your question, yes, there are methods of spinning up the ocean interior and tracers. And one of my colleagues, he will be talking, Keith Lindsay, he will be giving the BGC lecture. He's the expert on that. He works a lot on the Newton-Krylov schemes for spinning up tracers. So that's a great question to ask him. He might talk about, I'm not sure. So there are methods for spinning up the tracers in order to give you a quasi-equilibrium. Again, an area of very active research as well. It's a good question.
Any more question? Otherwise, Gustavo is going to stick a little bit, and you can ask more question in private. I want also to tell you, we have, if you haven't signed up for Meet a Scientist and you have regret, we have a few spots available today and tomorrow. Then check with Elizabeth or one of the admin at the front desk here. Yeah, don't feel online because I'm not looking at this anymore, but you can go and they have a few spots left. Okay, thank you.
Thank you.
Okay, thanks for coming back. Then, yeah, then thanks for coming back. We are going to have the second lecture from the ocean group. Then it's Peter Jen who will speak about parameterized physics. Thank you. You can, yeah, yeah.
Okay. Hi, I'm Peter Jen. I've been in the ocean section.
Wait, I think you are not on.
So I'm so old, all this modern technology is above my head. I've been in the ocean section for a long, long time. And I've been retired for 6 years. So when I looked at the slides last night, I realized how old most of the slides are and the parameterizations I'm going to talk about. So you need to regard this as a history lesson. But it's all very relevant. So there are a number of parameterizations that we make in the POP2 model. Vertical mixing is one of the most important ones that Gustavo talked about. Strong vertical mixing in the surface of the ocean, weaker surface mixing below. And lateral mixing, what the effects of mesoscale eddies are. These are the two most important parameterizations, so I'm going to spend all my time talking about them. So the vertical mixing scheme is called the K-profile parameterization, KPP. It's first published in a publication in 1994, so 30 years old. And what it says is that unresolved turbulent vertical mixing due to small-scale overturning motions are parameterized as a vertical diffusion. The ocean is different than the atmosphere in the sense that it is totally forced from the surface. In the atmosphere, you get forcing all through it, especially you get it at the surface, where you get deep convection, which is producing clouds and thunderstorms and whatever. In the ocean, it's all forced at the surface. The winds blow, they produce waves, they produce turbulence, and it mixes very strongly in the upper ocean, called the mix layer. Then you have a strong density gradient, called the thermocline. And below that, mixing is weak. As Gustavo pointed out, there's very little cross isopycnal. Isopycnals are the surfaces of constant density. There's very little cross isopycnal mixing in the deep ocean, which is why, as he mentioned, you can name water masses and they retain their properties for tens of years as they're going around the ocean. So that's a really important difference. So guided by our observations from the atmosphere, the rate of change of a variable, either velocities or TNS, is minus, this comes from the advection equation, the vertical derivative of the correlations between small-scale vertical velocities and small-scale variations in the quantity itself. And we parameterize that as minus a diffusivity times the vertical gradient of the quantity itself. So when you put that into this equation, you've got that d by dt, the rate of change of a quantity, is d by dz, a coefficient d by dz of x. So it's like vertical diffusion that we parameterize it with. But an innovation of the KPP scheme was that it was not only a vertical diffusion scheme, because it had these what are called counter-gradient terms, gamma x, in the temperature and the salinity. And this was the first parameterization to do this. So this was innovative at the time. And KPP involves three high-level steps. Determination of the boundary layer depth d, calculation of the interior diffusivities, which are small, and then evaluation of the boundary layer diffusivities, which are large. Boundary layer diffusivities depend on the surface forcing, especially the wind, but also the buoyancy. the boundary layer depth, and the interior diffusivity. And KPP produces quite large diffusivities below the boundary layer, which mixes temperature and salinity quite deep in times of very strong surface wind stress, such as strong mid-latitude storms. And this, with the counter-gradient term, is this thing working? Ah, I've lost it. And this was also an innovative part of the KPP scheme. So, how do we determine the boundary layer depth? So, it's determined as the minimum depth where the bulk Richardson number, RIB, in reference to the surface, equals a critical Richardson number, in this case taken as 0.3. So the bulk Richardson number is the difference between the surface buoyancy B, the buoyancy at the depth D, D itself, divided by the square of the difference of the velocity between the surface and the velocity at depth D. So what you do is you go down to the upper layer, you see whether this criterion, this Richardson number, is less than 0.3. If it isn't, you go down to the next layer. If it's not, so you go down until you find the first depth at which this bulk Richardson number is less than 0.3, and that is defined as the depth of the mix layer, where the mixing is strong above and weak below. And this is based on the stability of stratified shear flow, which depends on the critical Richardson number, and this time we've taken it as 0.3. And why this is used is that the boundary layer eddies, the vertical motions stirred up by the wind, with mean velocity VR at the surface and buoyancy BR at the surface, should be able to penetrate to the boundary layer depth, where they are first become stable relative to the local buoyancy and velocity. So this says you've got forcing at the ocean, strong mixing, till you go down to a depth where the velocity and the buoyancy at the surface are stable. That's defined as the mixed layer depth. You have strong density gradients across that, and then you're in the deep ocean, where viscosities and diffusivities are small. Now, they're small, there's many contributions, but they're all small. And because I've been cut down on my time from usual, I don't have time to go over those. So blame the lady in the front here. Now, in the paper by Large et al., they compare results from Ocean Station Papa, which is an ocean station ship that used to be maintained by the Canadian government west of Vancouver Island. And these observations from 1962. They kept the ship out there for a year, taking continuous observations. So these are over the upper 150 meters from March through March of the next year. So this shows that the boundary layer or the mixed layer depth shallows during the northern spring as the ocean gets heated and gets warmer and warmer at the surface, to a time in July and August where the boundary layer depth is a minimum and the sea surface temperatures are maximum. And then as fall goes on, there's less and less heat going in, and you get stronger and stronger storms. That's why I don't go out in the ocean. You get strong storms out there. And so you got vertical mixing. The depth of the boundary layer decreases, so it goes down from a minimum value of about 30 meters down to a maximum value of more like 100 meters. And then the density and the temperatures remain about constant, and then the cycle is repeated. Now, using the KPP, these were the values that they get. Now, if you read the paper, it says this is a really good comparison. but you can make up your own mind. The key was that it was better than any other vertical mixing that they tried and used. So KPP was an improvement over previous, simpler vertical mixing schemes. And it got used by several other climate models, but it's been a stable and constant in the ocean model since. Now, I want to go on to parameterizations of mesoscale eddies. This is my favorite parameterization, mostly because I was the person who came up with it, and I didn't start calling it, but after it got known and implemented in many ocean models, it's come to be called the Gent-McWilliams parameterization. So GM, don't think it's General Motors. General Motors, those cars get obsolete after 7 or 8 years. GM, first proposed in 1990, still going strong after 33. It's like the Toyota of mesoscale parameterizations. If you want to read about it, don't read this original one. Read this one in ocean modeling. After 20 years, I got asked to write a review. And it's in ocean modeling. And because it was after 20 years, I called it 2020 hindsight. Now, Gustavo showed quite a lot of these, which were better and newer than that. But if you run an ocean model at 1/10 of a degree, instead of more like 1 degree, which we do in climate models, then you get all sorts of variability in the ocean, as you can see here for the tropical Pacific. And this is the most energetic scales in the ocean are on the order of 1 or 2 baroclinic Rossby radius of deformation. Now in the atmosphere, the radius of deformation is on the order of 1,000 or more kilometers. And that's because it's proportional to the change in density across the fluid. And in the atmosphere, you go from surface density to almost nothing there. So you have a strong density gradient. In the ocean, the vertical density gradient is much, much smaller. It's only like 1% at most difference between the density at the surface and the density in the deep ocean. So the vertical density gradient is small, and so the Rossby radius is small. At the equator, the Rossby radius is on the order of possibly 200 kilometers. So a 1 degree model has a couple of grid points in that. And it's largest there because there the surface water is the warmest. As you go towards the pole, the surface water gets colder and colder and colder, so you get a weaker and weaker density gradient in the vertical. So the Rossby radius gets smaller and smaller, and in the very high latitudes, it's more like 10 kilometers. So a 1 degree ocean model cannot possibly represent those mesoscale eddies most energetic in the ocean. And here's just a plot showing a difference between 1/10 of a degree and a 1 degree. This is in the Agulhas current off South Africa. Still having trouble making this work, but there we go. So you need to do something in the ocean. So why is GM needed? So in the early models, you sure this is working?
Yeah, it needs a little bit.
Oh, here we go. In the early models, we used to have the z-coordinate models, and we used to have mixing along z-coordinates. As I've told you, that mixing really should be along isopycnals. And the rates of mixing are order 10 to the 4th along the isopycnals, order 10 to the minus 3 across them. So there's a 10 to the 7th difference in the magnitude of the mixing. So if you put something that's 10 to the 7th stronger here, and these slopes are 10 to the minus 3 at most, you get too much implied cross-isopycnal mixing from mixing along the horizontal surfaces. And 1975, Veronis showed that this produces spurious upwelling in western boundary regions, short circuits the North Atlantic, overturning circulation. So it was recognized that the tracer in z-coordinate models needed to be oriented across along the isopycnals, not along z-coordinates. So that was done in the early 1980s at GFDL. But what the GM parameterization says is, as well as this mixing along isopycnals, now represented by this row here, that the mesoscale eddies had an extra advection as well, U star. And the way we parameterized that was something to do with the slopes of the isopycnals in the horizontal and in the vertical. And that choice was made such that when you apply this, it reduces potential energy. Baroclinic instability, that's what it does. It reduces potential energy. So this scheme, by advection, tries to flatten the isopycnals and reduce the potential energy. So we'll go over that. So GM has by far its largest effect in the Southern Ocean. In the Southern Ocean, you have no land blocking what's called the Antarctic circumpolar current, which is the fastest and most volume current in the world's ocean, which are going round Antarctica, goes through Drake Passage, south of South Africa and Australia, and goes round. Has more like 130 to 150 spheredrops compared to the Gulf Stream, say, which has got a maximum of about 70. And because it's a continuous jet, it's much more, the dynamics are more like the atmosphere than the rest of the ocean where you're in mid-latitude gyres. So here's a plot of the Southern Ocean. So we've got Antarctica on the left, and the Antarctic circumpolar current is driven by a zonal wind jet in the southern hemisphere. So it's coming, the winds are coming from west to east, so they're coming out of the board. They produce a current, Antarctic circumpolar current, which is coming out of the board. And we're in the Southern Ocean. So Coriolis is turning things to the left. So under the center of the wind jet, these names, by the way, are North Atlantic deep water, Antarctic bottom water, ocean water masses are named. So under the maximum of the jet, you've got maximum velocities to the east in the ocean. So you have the strongest deflection to the left in Coriolis. And further north, where the winds and the ocean currents are weaker, you have a weaker deflection to the left. So you've got convergence of water right here. Convergence of water means it's got to go down. The opposite is true on the south side of the jet. You've got weaker Coriolis here compared to here. So you've got divergence of water here. So water's got to come up. So the mean flow is producing an overturning circulation that in this plot is clockwise. It's going down here and coming back up here. And that's what's tilting the isopycnals up. You have this mean flow doing this. Now remember that the eddy parameterization tries to minimize potential energy. And so it tries to flatten these isopycnals. So it's producing an overturning circulation which is in the opposite direction. So the two parts of the overturning circulation due to the mean flow and the eddies are opposing each other. So in the first time we implemented this in an ocean model, it was very crude, 4x3, just 20 levels. And the first thing he did when he got to NCAR, Gökhan did this integrations. So we ran to equilibrium, 10,000 years these solutions went, to a thing where we did one, where we used horizontal diffusion, as had been used before. And this is the overturning circulation it produces. So water's going clockwise around positive contours here, and anti-clockwise round negative contours. So you're producing divergence at the equator. And this is the overturning circulation in the northern hemisphere, which nearly always, all of it occurs in the North Atlantic. So this is the AMOC, the North Atlantic meridional overturning circulation. And here is that positive mean overturning circulation I just talked about. And beyond that is a negative circulation producing Antarctic bottom water. And equivalently, we ran a simulation that had GM, plus it had mixing along isopycnal surfaces. And if you plot the overturning stream function from the mean flow, it looks reasonably like this. And again, it still has this overturning circulation to the mean flow. But if you plot the overturning circulation when you add in the eddies, you get this. It has strengthened the AMOC from 14 to 16 Svedrups. But by far the dramatic thing is that it has eliminated this overturning circulation. So you've got almost no overturning circulation here. So the eddy overturning has almost exactly balanced out the mean flow overturning. And this has really important implications, because here you are advecting at the surface water from the south towards the north. So you're advecting cold water over warm water. That means the density at the surface is larger than the density just below. So you produce deep convection there. In this case, you have eliminated that. So what we found was you eliminate this deep convection. So when we plotted the deep convection that's produced by these two models, in the one with horizontal mixing, you have deep convection all over the place, especially in the Southern Ocean, just due to the what was going on that I just described. Whereas in the one with GM, you produced deep water formation in just a few locations in the ocean. In Greenland, Iceland, the Jin Seas here, in the Labrador Sea here, in the Weddell Sea here, and in the Ross Sea here. Now, if you showed these to a real oceanographer, someone who has a gray beard and goes on ships, and asked them which of these is more realistic, they would obviously say this one. Deep water formation, where things go down in the ocean, is known only to occur in these 4 locations. So this was a big surprise to us. This is the favorite plot of my career. So the GM summary, it mimics the effects of unresolved mesoscale eddies as the sum of diffusive mixing of traces along isopycnals, but with an additional advection of traces by the eddy-induced velocity. The scheme is adiabatic, and therefore it's valid for the interior. You expect GM to occur and be valid below the thermocline in the deep ocean where the mixing is small. It is not valid in the mix layer where mixing is far too strong. It eliminated any need for horizontal diffusion in z-coordinate models, so it eliminated that Voronezh effect that I briefly described. And this implementation of GM in an ocean component was a major factor enabling stable coupled climate models without flux adjustments. It's not clear to me how many people know about flux adjustments these days, but before this run, every climate model that was run, if you started from a realistic simulation and ran without flux adjustments, it would go away from that realistic simulation and drift, in many cases, quite strongly. Some runs you've seen, they only go a few tens of years because then the climate has drifted so far from the initial condition. This CESM version 1 was the first one that could maintain the temperature distributions in the ocean and the atmosphere without flux adjustment. Here's the plot from there. And the ocean had quite a lot of variations, but if you calculate any drift here, it's small. In fact, the drift depends on exactly where you calculate the drift from. So this was the first time this had happened. At a meeting in Boulder about 2 years before we started this and got this result, was a talk by Suki Manabe. Suki Manabe is a famous person from GFDL who won the Nobel Prize 2 years ago from his contributions to climate. After his talk, I asked him whether climate models would ever be able to run without flux adjustments. And his answer was categorically no. So this was a big surprise and a big deal. So big surprise and big deal, what do you do? A few of us wrote it up and submitted the paper to Science. It was rejected. One of the reviewers said we had used restoring to salinity during the run. Now, it was true that we used restoring to salinity to spin up the ocean component, as you need to, but during the integration, there was no restoring to salinity. So we wrote back to the editor and said, well, this review is wrong. There is no restoring to salinity during the run. And their editor wrote back and said, it's still rejected. So the most important result that I've ever got in my career was the first paper I ever got rejected. I did not submit anything to Science since. This was so important that people got a hold of it. Other modeling centers started to put GM in, and either they could then run without flux adjustments. The Hadley Center was one of the first to do that. The Australians put it into their model, and the flux adjustments they needed over the high latitude Southern Ocean went from a maximum of 250 watts per square meter to 25 watts per square meter. So it's that overturning in the Southern Ocean, preventing that advection near the surface, that changes the whole situation and enables these models now to run without flux adjustment. It's still only 1 minute to go, so I've still got time to tell you that when we announced this, the then director of GFDL wrote to our program manager at NSF saying they must have cheated. This could not be done. I don't know who he asked, but Manabe was probably the person that told him that. And he wrote and said, they couldn't have done this. It can't be done. Well, it could be done, and it was done. This was the first one. So that's a bit of history about the first. And the CSM project has never, ever used any flux adjustments. Now, 20 years ago, I was asked to give a talk about this at Limerick in Ireland. Now, Limerick is famous for limericks, so I could not resist making up a limerick for my talk. So all limericks start off with something like this. There once was an ocean model called POP. You know, that's sort of traditional. That's how they start. And how does it finish? There once was an ocean model called POP, which occasionally used to flop, but eddy advection and much less convection turned it into the cream of the crop. Thank you.
Yes, thank you. I love, yeah, I have seen this before, but each time I found this so good. Any question for Peter?
Thanks, Peter, for a good presentation. And just on a lighter mood now, when do you plan to resubmit the GM paper?
So, because we got rejected by science, we then wrote up a much more complete paper about the CSM version 1. And that paper had more authors. It talked about all the things, so it wasn't nearly so short. And that was published in the Journal of Climate. Byron Boville and I were the lead authors on that. So it did get published, but it was not in Science. So.
Hey, thanks for the talk. I'm wondering, so obviously the same physical argument for why there's an eddy correction to the overturning circulation in the Southern Ocean, there should be, the isopycnals will want to flatten in the Northern Hemisphere as well. So why do you still have an AMOC that's strong in the Southern Ocean? And like, is there still an adjustment that's happening due to the GM parameterization, and is it just not fully canceling out?
Yeah, so it's strong. If you remember that plot, the AMOC went up actually from 14 to 16. So the deviations of the isopycnals in the Northern Ocean are nearly as strong as in that Southern Ocean. I'm getting this the right way. And also the mid-latitude dynamics don't let the eddies be as important. Technically, if you integrate the zonal momentum equation, because you're going round the ACC, you have no contribution in the zonal integral from the pressure. In a mid-latitude gyre, if you integrate across the gyre, the pressures on the two sides of the ocean are different. So pressure term comes in the zonal integral of the momentum equation. So the dynamics are different. So if you look at the GM overturning circulation, Northern Hemisphere, it's 2 or 3 Svedrups. In that Southern Ocean, it's more like 20. So it's by far the largest there. And it's because of the zonal continuation of the current.
Okay. And then in Gustavo's talk, he talked about different schemes for vertical profiles. And I was wondering how this parameterization works if you're using a sigma coordinate or an isopycnal coordinate versus a z coordinate.
You just have to evaluate the density gradients in those different coordinates, and it's much simpler if you've got an isopycnal coordinate in the deep, because then the mixing is along the grid lines, so you get less implied cross-isopycnal mixing. And evaluating the density gradients, the horizontal vertical, is much more straightforward in a isopycnal model there. So there's big advantages for using isopycnal coordinates in the deep ocean. The trouble is at the surface, then they surface. So, what the isopycnals are in the tropics, come to the surface. So when you're dealing with strong mixing in the upper ocean, Z coordinates are by far the best to do. So somehow then you have to go from Z to isopycnal, and that's the art, that's the skill. And Gustavo's skillful. Me, I'm old and no skillful anymore.
Thank you.
Hey, thanks for the really interesting talk. As an atmosphere person, I was curious. This parameterization deals a lot with baroclinic instabilities, and I was wondering what are the implications for barotropic instability and the eddies arising from that?
Yeah, so this parameterization just addresses baroclinic instability and doesn't do anything about barotropic. Some people have tried to do something about that, but in that Southern Ocean, baroclinic instability is by far the most dominant thing. In other regions of the ocean, barotropic instability comes in, but this parameterization doesn't address it. And the key to it, the key to the form we chose was to reduce potential energy. One of the slides I didn't show, missed out, we did a simple thing where you had a front to start with, you let the eddy go, and in the end, the equilibrium position was where all the isopycnals were flat. Then there's no eddy velocity, and potential energy is at a minimum. So that's a stable final result of what the eddy parameterization does to a front. So it takes the fronts out. The wind and the mixing is what puts the fronts there. And the fronts get there because of the geostrophic flow, d rho dx, to u to z.
Thank you.
Any more question for Peter? You should not be shy. I should tell you the first question I asked to Peter. You probably don't remember, but I was a young scientist, probably your age, and I was doing mainly cloud microphysics and atmospheric thing. And I met Peter, and he was giving a talk, and I asked him what was the G in the GM parameterization. And he saw I was kidding, and I was not. And when he realized, and everybody was embarrassed, but we are still friends. But I cut his talk now, yeah.
I'd forgotten that.
You forgot this?
Yeah, I forgot that.
Each time I would see you, you will give me a hard time.
Hi, thank you for the talk. How do you feel about the, I guess, capabilities and potential success of machine learning based parameterizations compared to parameterizations like the ones you wrote that are, more physics based or were directly derived?
Yeah, so that's something that's come in the last several years. And in fact, if you want to know a lot about that, you should ask Gustavo. I haven't done anything on that. But what they do is you run high-resolution ocean models, and then by machine learning, you learn what those eddies do realistically. And then you go back and run a lower resolution model, putting in what the eddies' effects are supposed to be. So there's two advantages to that. One is you do get higher resolution effects in, and B, you can run that much, much faster than the full ocean model. So it really has a lot of potential to speed up how we do ocean modeling with realistic implications. Why you can't do models with, quote, ocean resolving resolution of a 1/10 of a degree regularly is that compared to a 1 degree, you've got 100 more grid points, and the time step is a 1/10. So a 0.1 degree model takes 1,000 times as much computer time as a 1 degree model. But as time's gone on and computers have got bigger and bigger, there are now more and more integrations using ocean resolving, eddy resolving ocean models. CSM has quite a lot. And at the conference this year on the CSM, actually I was impressed by some of the real improvements that are made. We're using this eddy resolving models. You know, parameterizations aren't as good as the real thing. So the more and more you go, the more runs that are done with eddy resolving resolution, the less that GM will be used. But it's still used in all climate models that have a resolution above or greater than 1/4 degree. So I'm not quite over the hill and redundant yet, but it's coming.
Any more questions for Peter? And you should know also that he's an expert in ocean and he also an expert in Limerick, but also he's one of the most well-known person in bird. He knows everything about birds and also cricket, not the animal, the sport, cricket. Is it? Yeah, then if you have more questions about ocean, Limerick, bird or cricket, can I ask you to stay here for during the break?
Yes, just because it's you.
Sorry?
Just because it's you.
Yeah. Okay. Thank you. Thank you then. There will be a few more bagel when you come out. They were supposed to put 80 by 4 piece of bagel, and it seems we didn't have our count. And if you want to get, I was told there will be more bagel when you get out of the room. And also one more announcement, then there are only 2 scientists that have still spot left. It's Brian Dobbins. Brian Dobbins, he has 2 spots left for today, meet a scientist, and he's really an expert on everything that's software engineer, cloud. He's really amazing, and you have seen him in the lab. And then there is also Günther that does Landice. I know less people have interest in Landice, but he's also very involved in early career professional development. Then if you wanted to talk with him about this, he's the co-lead of the early career development section here at NCAR. Then, yeah, just an announcement. There are 4 spots left for today at lunch. And again, if you are meeting a scientist, leave the lab just at noon, and the other wait a little bit more to give priority, then people can have their lunch with the scientist. Okay. Then I'm going to, yeah, I don't know why I speak in 2 mics. I really want to be heard. Okay, then today I'm going to give you the introduction to today practical. And basically what we are going to do today, I didn't do a single chapter, I did 3 chapters. We will talk about name list modification, also troubleshooting when the model crash, what should I do? And we also take the next step when you start to modify the model itself. And I want to say this because I can stand here and talk about CSM for days, for weeks even. I love CSM, but I think you will not really learn much by listening to me. You really have to go and play with your little finger and type and make mistake and make the model crash. It's how I learned CSM. I have been here for 20 years, and this is really the way I learned. I can just show you the door. The rest, it's yourself. Okay, what we are going to do today, then the name list modification, troubleshooting error, and the code modification. Then this is in your book. It's the 3 sections over there. There are a lot of exercise. I prepare tons of exercise, but you don't have to do everything. You can move at your own pace. It's just that you can always come back later to this. Then what are name lists, how to modify them? Then, for example, right now, you have been outputting monthly mean. The model by default is going to output monthly mean. But then if you look at the daily cycle, it's useless. Then how can you change the output frequency of the model to output daily or 3-hour output instead of monthly mean? Then it's what you do in the name list. Then basically, here I have been doing a lot of this kind of plot. It's to show you, I'm very visual, to show you where you are in the directory and what it does. But this is, yeah, there are all these views inside the documentation. The next thing the next chapter, it's your run crash. And we are going to make a crash in purpose. I will make you output a variable that doesn't exist, and the model is going to crash. And then this is usually, there are ways to find information. I have picked an example that it crashed and it's give you useful information, because sometimes the model crashes and you are looking at the log file and you really wonder, yeah, you cannot find any useful information. This one you will find useful information, but it will give you guidance to see how we debug when the model crashes. Yeah, then it will be the log file, also adding some debugging info, and this is the exercise of you. Then you go again step by step in this chapter, and then until you reach the exercise. The last thing is the source modification. Now, if you are bored and you want to go to the next level, let's say you want to add a variable in CSM that doesn't exist in the model. And I say it's the choice between the red pill and the blue pill. And it's this in the movie Matrix, the main character is offered the choice between a red pill and the blue pill. And basically the blue pill allows him to remain in the matrix. It's what you have right now, a fictional computer-generated world called CSM, and it's really easy to use. Once you take the red pill, it leads to your escape from the matrix into the real world, embracing the sometimes painful truth of reality. Then when you start to modify the code, adding parameterization, it starts to be harder, but it's really also fun and interesting. Then in the example here, we are going just to add a variable in CAM. A lot of my examples are coming from CAM because I'm the liaison for the atmospheric model. But everything, a lot of stuff you learn also are transferable to other component. You will not add a variable in MOM or other model the same way, but it's the idea how you modify code. Again, you go step by step into the chapter, and then you reach the exercise. And then question, then people, I'm going to say, I haven't finished Monday exercise. What should I do? Then I want to reiterate, this is not a race. And we are not rat, obviously. Then it's not a race. You should move at your own pace. We are coming from all different levels. We want to give you this week the tool to start building knowledge on CSM. And it's slow. You cannot learn everything in 1 week. I have been here for 20 years, and I'm still learning everything every day. Also, I have already completed all the chapter, what should I do? Then you have people who have been running already the model before, and they will move faster, but you can help the person next to you. I can tell you that you are learning a lot by running CSM, but also you are learning a lot when you are helping somebody else. Then I found it very useful. And the last thing is a question I'm completely confused about the tutorial special queue. What should I do? Then once again, the information is over here. It's also in slide that I have put. Then if you are not sure which queue you should be running, call one of us or call me, and we will help you with this, okay? Okay, this is all I have. This is again my, oh, I didn't put this little acknowledgement, but yeah. Any question? Otherwise, yeah, please, you can sign up for one of the four spots left. First come, first serve, and otherwise we will meet in the library. There should be some bagel. I hope that I'm not lying. They told me there will be bagel here. Yeah. Yeah, it's not me. It's not me who did this. Yeah. Yeah. Okay, then welcome back. Does it work? Okay, welcome back, everybody. Hello. Hi, hi, hi. Can somebody make a big noise? Okay, guys, can you listen? Okay, let's go quiet. Yeah, the funny thing here, then Keith noticed that we went back in time. I don't know who created this slide, but we are in June. You didn't know it was possible, it is. Okay, then we have our last ocean talk, and it's going to be given by Keith. That's going to talk about the biogeochemistry. Then Keith, you can come here. Yeah, and you have 30 minutes.
Does that work well? Good. Thanks, Paul. I'm Keith Lindsay, as Cecile mentioned. I work here at NCAR in CGD in the oceanography section, and I work mostly with the ocean biogeochemistry model, though I have dabbled in lots of different parts of CESM over the years. I'm going to talk about biogeochemical modeling in the ocean, and time permitting, I'll get into some aspects of the carbon cycle modeling in the coupled model. So a brief outline of what I'm going to talk about in this time are some of the large-scale ocean biogeochemical features that we try to capture in our models. In order to trust that our models are doing the right thing, we want to make sure that they reproduce the major observed features, and so I'm going to review some of the major observed features and talk about some of the processes that lead to those features, and those are the processes that we put into the models. I'm going to do a bit of a deeper dive on the techniques of modeling biological productivity within the ocean, which is just one process out of many that are in an ocean biogeochemistry model. Talk about some of the ways that we assess skill of our ocean biogeochemistry components. And then talk about the global carbon cycle, which the ocean carbon cycle is one component of, and then wrap things up with a summary. So my talk starts with observations, because we want our model to reproduce what's going on in the real world. And so I've got a few things here. Does this have a pointer that, let's see. There we go, good. These are two transects in the Pacific Ocean going from the Aleutian Islands in the north all the way down south to the Antarctic coast. And these plots are latitude horizontally and depth vertically. And the top panel is nitrate. Nitrate is a nutrient in the ocean. This is something that biological critters need for growth. And when they grow, they absorb this into their cellular membranes to form DNA and other sorts of cellular membranes. And then the bottom panel is oxygen, which when there's photosynthesis going on in the ocean, oxygen is produced. When organic material is remineralized back into inorganic forms, oxygen is consumed. So there's a bit of an inverse between the two of these, the nutrients and the oxygen, and I'm going to go over some of the major features that you can see by looking at these and talk about the processes that contribute to these features. First, in the near surface waters, so this goes down to around 6,000 meters depth in the very near surface waters. You're right, there's a delay. Nitrate is depleted. Very, very low values of nitrate, excuse me, in these temperate latitudes. And that is because the biological activity consumes nitrate until there is none left. And that happens in the near surface waters because that photosynthesis that is fueling cellular growth requires light. And light is attenuated at depth, and so that photosynthesis only happens in the top, what's called the euphotic zone, which tends to be like in the top 100 meters or so of the ocean. So nitrate is depleted in the very top levels. If you look, but it's not, one thing that you might notice is that it's not uniformly depleted at all latitudes. Near the equator, there's not nearly as much consumption of nitrogen, and that's because there's other things that are going on that are limiting biological activity in the right around the equator. In the instance here, that is the availability of other nutrients. In particular, iron is a micronutrient that is required for biological growth, and it is limited in the equatorial regions. And so biological productivity ceases when they run out of iron and there's some excess nitrate left over. So that's why in the tropics, there's more nitrate. It doesn't go all the way down to zero. You might also see that in the high southern latitudes, there's also lots of nitrate. And part of the story there is also, again, that there's not enough iron to fully supply biological productivity in the Southern Ocean. And there's also not enough light year-round in those regions. And there's also, in the wintertime, there's deep mixing, which puts those critters down to, well, there's two things. One, in the wintertime, there's not much light in the winter. And deep mixing moves those critters down to depths where even if there's light at the surface, there's not light at depth because of the mixing that happens in the wintertime. So there are these properties that limit biological productivity at the equator and at high latitudes. Moving away from the surface layers, what happens when the critters are growing, they form organic matter through that fixation of carbon and nitrogen and other nutrients into organic matter, their cellular membranes. When those critters die, they go through their life cycle, and this might be natural death just from mortality. It might be from viruses that infect them and they die, or they might get eaten by bigger creatures up the food chain. Some of the organic matter, what happens to that organic matter is that bacteria will break it down back into inorganic forms. But sometimes that organic matter, before that breakdown happens, it can sink. And when it sinks and then is converted back into an inorganic form, that increases the inorganic nutrients at depth. And this is something that's called the biological pump. So the nutrients are consumed at the surface, the critters die and sink through various mechanisms, and then they remineralize at depth. So they're moving that inorganic nitrate from the surface to depth. That's called the biological pump. So that explains partly what's going on with these elevated nitrate values in this 1,000 to 2,000 meters. That reintroduction of that inorganic matter attenuates with depth, and so some of it, the deeper down you go, there's less of that sinking matter that gets to the depth, and so there's not as much of that remineralized nitrate into the depths of the ocean. But that's not the whole story here also. There's a latitudinal variation going on here with nitrate. And that is because of the overall large-scale circulation within the ocean. In particular, in the Pacific Ocean, you've got deep water forming in the high southern latitudes, and that is moving slowly northward into the deep North Pacific until there's return flow moving north. And so the waters that are farther north are older. They've been removed from the surface waters for a longer amount of time. They've had more time to accumulate respired, regenerated organic matter, and so they build up more organic matter at the north end of the Pacific Ocean. There's less time in the Southern Ocean for that buildup of remineralized matter to happen. So that are some of the processes that are contributing to what the features that you see in the top panel. The bottom panel is almost exactly a inverse of that, but there's more to it than that. So, as I said, when there's biological productivity, that produces oxygen, and when there's remineralization of that organic matter into inorganic forms, that consumes oxygen. And so largely you see where there's this large regenerated nitrate in the North Deep Pacific, there's corresponding low values of oxygen because of that remineralization consumes oxygen, leading to low values. But there's a bit more to it than that, and that is, if you look at where there's really, really low values of nitrate near the surface, there aren't uniformly really high values of oxygen, whereas if photosynthesis creating oxygen was the only story, you would accept it to just be an inverse relationship. But there's more to the picture here, and that is that oxygen is exchanged with the atmosphere through air-sea gas exchange. And that air-sea gas exchange depends upon the temperature of the seawater. Cold water holds more dissolved gas than warm water. And the air-sea flux tends to bring the concentration of dissolved gases closer to an equilibrium solubility concentration. And so you tend to get really large values of oxygen in the Southern Ocean where it's cold, and also in the north because of that temperature-dependent solubility in the gas flux. And there's lower values at oxygen right on the equator where the water tends to be warmer. And then you have the overall large-scale circulation going on very similarly to what's going on with nitrate. This is called the National Center for Atmospheric Research, and you might wonder, why are we doing ocean biogeochemistry at the National Center for Atmospheric Research at an altitude of 1 mile, really, really far away from the ocean? Because it's fun. Well, also because the ocean plays a big role in setting atmospheric concentrations of carbon dioxide, which is very relevant to the global climate, something you might have heard about here or there. And so what I'm showing in this plot is very similar to the previous plot, where I'm looking at something called dissolved inorganic carbon, which you can think about it as dissolved CO2 gas in the ocean. CO2 gas dissolves in the ocean seawater just like oxygen does. And DIC is a mix of the processes that govern DIC are a mix of those that are like the nutrient, nitrate, and the oxygen gas. When critters, the features that are like nitrate are that when critters grow, they assimilate DIC into their cellular membranes, and so they consume DIC. And so you see similar low values in the, catch up, you can do it. Low values right near the surface of DIC from the photosynthesis, and you see the elevated values of DIC where there were elevated values of nitrate. But there's also air-sea gas exchange with a temperature-dependent solubility like there is for oxygen. And so DIC also has some characteristics that look more like a dissolved gas, like oxygen does. And so that leads to this higher values at high latitudes where it's colder. So DIC sort of fits in between the two tracers of nitrate and oxygen. And that's what is climactically relevant. So some people can learn well from pictures. Actually, before I'm getting ahead of myself. That air-sea gas exchange is, there are enormous number of measurements of that in the ocean. So talking about, this is another observed features of the ocean that we try to capture within our ocean biogeochemistry model. So this is a map of air-sea gas flux spread out over multiple years. And this is an older product, it's not the most recent one. But these red values are outgassing of CO2. And where this is going on in this equatorial Pacific is that cold old waters are upwelling on the equator, and they have lots of carbon in them. And when they hit the air, they start warming up, and that solubility reduces the equilibrium solubility concentration because as it warms, and that leads to an outgassing of that respired carbon into the atmosphere. And so that is why we have outgassing of carbon In the low latitudes, we have uptake of carbon, this blue color, intermediate values, and then in some high latitudes where we have subduction of water into the abyss, we also have uptake of CO2. And this is where things become climactically relevant. So pictures are great for looking at things. I'm going to overview it because you also I'm going to hammer it home about these different processes that are going on governing the distribution of the nutrients, oxygen, and carbon. There's biological productivity in the euphotic zone where there's light. This consumes nutrients and inorganic carbon. This produces organic matter and oxygen. There's export of organic matter out of the euphotic zone through sinking particles, such as like detritus, portions of their critters that die and they sink. There's large, up the food chain, you've got literally critters are pooping. And so that's also what's going on, is that stuff sinks through the water column and exports the organic matter out of the euphotic zone. Some organisms also create shells, whether they're made out of calcium carbonate or silica shells from diatoms. Those sink out of the euphotic zone because they're more dense. There's also circulation of suspended matter that leads to export of organic matter out of the euphotic zone. That organic matter remineralizes back into inorganic forms. This is sort of the reverse of productivity, and it consumes oxygen. And then there's general circulation on top of that. There's advective transport, and then there's also lateral and vertical mixing. And then on top of all of those is temperature-dependent air-sea gas exchange. So that in order to have a model that reproduces all of these observed features, we have to have parameterizations of all of these processes in our model that we then need to vet against observations themselves with a process-oriented model, and that's how we reproduce the observed patterns of the ocean. There's more to the picture. Those are the very large-scale features that are visible. There's also some other features that are not necessarily so relevant globally, but locally can be very significant. One is atmospheric deposition of nutrients. Nitrogen can be deposited from the atmosphere. You can get iron deposited from the atmosphere from black carbon and dust sources. Phosphate can come from the dust particles as well. So we have iron, nitrogen, phosphorus, et cetera, is introduced to the ocean through atmospheric deposition. There's some of the sinking particles in the ocean get all the way down to the seafloor. I talked about that flux attenuates as it moves through the water column. Some of it does reach the seafloor and is buried and only gets reintroduced into the system on very long geological timescales. Typically, when we're doing climate models, we're not looking at timescales of geological timescales like millions of years, but it is irrelevant on long timescales. There's also riverine inputs of iron, nitrogen, phosphorus, carbon, oxygen, et cetera, which matter locally in river plumes. There's also nitrogen fixation, which is important in the nitrogen budget. So the part of the nitrogen, there are some critters that usually they just consume nitrate, which they can readily assimilate into their cellular membranes. Some critters can dissolve nitrogen gas, which requires a lot of energy and it requires special cellular processes to do that. It requires a lot of iron. This converts that dissolved nitrogen gas into ammonia. And then there's a reverse of that denitrification when there's organic matter being decomposed. If there's no oxygen to fuel that process, usually then that bacterial process will consume nitrogen instead of the oxygen. And so that has a sink of nitrogen in this ocean model. So that's sort of like large scale what we do in the models. And I'm going to move on to how do we model biological productivity in the ocean model. And one of the classes of models that we use in CESM is something called the NPZD model, because I'm using this acronym because I'm sure you haven't heard enough acronyms this week yet. What NPZD stands for is a nutrient, phytoplankton, zooplankton detritus. And so typically you've got one or more nutrient pools that are represented in an NPZD model. You have one class of phytoplankton. These are the critters that do photosynthesis. Then you have one or more classes, categories of zooplankton. Those are grazers that eat the phytoplankton. And if you have more and more types of zooplankton, they might eat other zooplankton going up the food chain. And then you have detritus, the stuff that can sink. And then a canonical model of a simplified model of this is illustrated in this diagram to the right, where there's a phytoplankton box and a zooplankton box, well, I should shape circle. And these arrows are representing different flows of matter from one pool to another. This ammonium and nitrate are two forms of nutrients. And so you see that there's an arrow going from nitrate up into phytoplankton. That is the biological productivity. There's an arrow going from phytoplankton to detritus and zooplankton, so there's grazing and death. This model also has bacteria and dissolved organic matter. And then there's recycling back down to the ammonium. This is a very simple model. We have a much more complicated model in CESM that I won't show you the diagram because it's just too much. So in a very simple model, just to represent these processes, we use mathematical equations to represent things. And so this is now just a NPZ model. So there's a N for nitrate, P for phosphorus, Z for zooplankton. And there's all these different terms here that represent things like productivity. This is the growth term of phytoplankton, which has a bunch of different terms representing nutrient limitation, light limitation, and a growth rate. There's grazing, which depends upon the phytoplankton and the zooplankton. There's mortality of zooplankton. There's growth of the zooplankton from their grazing of the phytoplankton. And then there's also all the same terms appearing for nitrate. If you spent enough time looking at these equations, what you might see is that for every term that's in there, there's a negative of it elsewhere in the equations. And so this has a closed mass budget for nitrogen. Something that goes from one pool to another, it loses it here and gains it here for each process. So that's the bottom line of mass conservation. This is a very, very simple model. But if you count all of the parameters in it, I haven't recently counted, I don't remember, but I think there's over 10 different parameters for this really simple model. So how do we estimate these models for our climate models where we put these in? And so when we have our full-blown model with many more equations, many more boxes, there's many more parameters, and we have to estimate, we have to put values into those equations. So how do we do that? I went a little bit out of, something went wrong. There it is, okay. We estimate those from observations where we measure processes out in the field or in laboratories. We might look at photosynthesis irradiance curves, look at nutrient uptake curves, so what happens if you add more nutrient to a reservoir, how does the photosynthesis change? You can tune or optimize these parameters to improve your model's comparison to field data, and then sometimes we might just use the value that we used in the previous version of the model. There's lots of, so this is a involved process to get these parameters to reproduce the observed patterns of the real world. I mentioned that there is that simple model of the NPZD as well as a NPZ model where I showed the diagram. These generalize to something called plankton functional types, where what we do is we can't have, there are perhaps like millions of different species of phytoplankton in the ocean. We do not represent all of them in our models. That would be computationally impossible to handle. So what we do is we categorize large number of species of phytoplankton into one box and say, well, these are called functional types. And so we might have critters that, and here are some of the descriptions about how we group those categories of phytoplankton into different groups. So it might be based upon their nutrient needs or their distinct behaviors that they have. For instance, maybe they make calcium carbonate shells, and so we put all of them into the calcifying box. Or they make silica shells, the diatoms, and we put all of them into a diatom box. There are thousands and thousands of species of diatoms, but we put them all into one box. And so this adds to some uncertainty with those making those parameters. And so that's where we have some wiggle room in specifying how we will tune the model to reproduce observations, even though we are oversimplifying the representation of the biology in the model compared to what's there in reality. One of my favorite studies is looking at complexity of models in how well they do in different scenarios. And I'm going to have to go through this quickly because I spent too much time on the first two slides. And this gets into a fundamental question of, you're here learning about CESM models. One question is, what is the best model? The simple answer is it's CESM. But no. The real answer is it depends. And that's the answer to a lot of questions. And what this was a study by Friedrichs et al. I don't have the, there it is, there's the reference down at the bottom, where Friedrichs looked at a dozen different models, and they looked at observations of productivity. There are models of very different complexities. And these are numbered 1 through 12, and the higher numbers have more complexity. And what Friedrichs did is looked at, well, how well does the model do at 2 locations in the ocean? There's a EP, which is in the equatorial Pacific, and AS is the Arabian Sea. And Friedrichs took these untuned models, and this just giving the tuning parameters that were given to her by the model developers, and found that the simple models didn't do so well, and the complex models did better, given the default parameters given by the model developers. But then Friedrichs said, well, I'm going to tune the parameters to improve the simulations. And when Friedrichs tuned these to look at, well, what if I just look at the equatorial Pacific or the Arabian Sea and tune my parameters individually for each one, the low complexity models, which are inexpensive to run, did generally just as well as the complicated models. And so if all you want to do is a model that works in the equatorial Pacific, you don't need the Cadillac model. You can use the simplified model, the Ford Pinto or something. If that's all you care about is one location. But now in this bottom left, if you try to work in both locations simultaneously with the same parameter sets, then you start to see that there's a benefit to the more complicated models. And then if you actually want to use the tuning from one site and optimize at one site and then run it at the other site, you see that then the complicated models really start to shine compared to the more simple models. And so if you need a model to work globally or in different climate regimes, for instance, you get some benefit from those more complicated models compared to the simple models. And so there isn't, part of what is the best model, part of the depends is, what are you trying to do with the model? If all you care about is one location and one climate regime, you can use the simple model. But if you're looking to do something, a global model in different climate regimes, then the more complicated models tend to do better. This is a diagram of what is in the CESM model. This slide needs to be updated because it says CCSM, which was an acronym that we used about a decade ago, excuse me. And I'm going to skip over the details of this. This is just showing that we have many more boxes in our model than with those very simple models that I showed in the first slides. Some of the features that we have in the CESM BEC model, so I've updated the acronym to CESM here. We have 4 nutrients, we have 4 elemental nutrients of nitrogen, phosphorus, silica, and iron. We have 4 phytoplankton functional groups, 3 autotrophs that photosynthesize, and a grazer. There's an implicit representation of calcifiers, coccolithophores, and there's 32 tracers in the model, much more than that 3 when I had 3 equations. There's some simplifying assumptions in the model, like there's fixed carbon to nitrogen ratios in the plankton, but there's variable ratios for some other ratios of elemental quantities in the phytoplankton themselves. And the iron is a pretty sophisticated state-of-the-art model of the iron of the ocean that we have in CESM. And iron is bound to something called ligands that helps improve our representation of iron. Some things that we don't represent in our model is that calcification and dissolution of calcium carbonate are independent of sort of the carbonate chemistry of the ocean, whereas in the real world they do depend it. Riverine inputs of BGC tracers are prescribed and they are not coupled to a land model. All the things that get buried to sediments in our model are lost from the system forever. We don't capture those geological timescales that sediments return back to the system. We don't have any treatment of biogeochemistry in the sea ice in CESM. There's work ongoing to couple sea ice biogeochemistry to ocean biogeochemistry. And the focus of this model is on lower trophic levels because that's really what's needed to capture the ocean's control of carbon dioxide concentrations in the atmosphere. Gets back to National Center for Atmospheric Research. We validate our models by looking at macronutrients to various observational data sets, the World Ocean Atlas, like phosphate, nitrate, and silicate. In oxygen, we can compare our model results to these well-established climatological gridded data sets, as well as carbon and alkalinity to GLODAP analysis. We can compare our surface chlorophyll to satellite measurements, and also the productivity of the ocean model can be compared to estimates from the satellite as well. So we have global coverage of those observations. CO2 flux can be compared to observational products, some of which have been expanded from point observations to global data sets using neural nets. And then we have observational databases of iron observations. It's much more complicated to measure iron in the ocean than it is some of these other quantities. And so here's an example of looking at that air-sea gas flux. In the top left is a CESM2 air-sea CO2 flux in a 20th century run compared to a neural net filled estimate of the air-sea CO2 flux spatial map annual mean. And then on the next two panels is a latitude map with a monthly averages going across. And we capture the major features of the air-sea CO2 flux that are in the observations. There are a bunch of challenges with these. Optimizing the BGC parameters to best match OBS. Success functional group approach increases the uncertainty between observations of individual creatures and what we have in the model. And we also have biases in our physical model that impact the biological simulations. And so there's some trade-offs of tracking down or the errors in the model due to biogeochemical representation or physical representation. And also then spinning up the model is a work in progress. I'm really short on time, and so I'm going to kind of skip over the global carbon cycle. I will say that we do simulations of the global carbon cycle in CESM. This is an earlier version of CESM showing the integrated fluxes of CO2 into the atmosphere from different reservoirs. In the bottom right, D is from the land to the atmosphere, and then the gray bars are observational estimates. So the model is doing a reasonable job of capturing the land air CO2 flux. And then the bottom left is the air sea CO2 flux. Bottom right is fossil fuels. This is reading fossil fuel emissions from a data set, so we better match OBS because we're just reading what the OBS were. So it's good that we match them. And then if we add them all up and then see, well, what is the resolved impact of air-sea atmospheric concentrations of CO2, how they vary in time, we're doing a reasonable job of matching that in this version of the model. We can compare that also to atmospheric CO2 seasonal cycle at various locations around the world, and the model does a reasonable job of capturing the seasonal cycle of CO2 in these different regimes, like up in Alaska, Mauna Loa, Hawaii, and then in the Southern Ocean. If you really want to dig into the literature on carbon climate feedbacks, I included a bunch of references here for literature. If this is really what you're interested in pursuing with your studies, here's a list of the literature on this thing that would be of interest to you. And I'll leave the summary up there, which is just recapping what I've said, and then we can do questions.
Thank you so much. Yeah, question? Okay, 1, 2.
Thank you so much. I was wondering, I don't know much about how like biogeochemistry varies over deep time and stuff, but I was wondering, yeah, if there's any kind of paleoclimate, um, like, like whether you can do like paleo biogeochemistry, or like whether that's even relevant.
There's certainly much interest in doing ocean biogeochemistry in paleo regimes. One of the challenges there is we can spin up, it's very computationally expensive to spin up the model. And so if we spin it up to a pre-industrial state, that takes a lot of effort and computational and wall clock time. If you go to a different climate regime, like in paleo times, that has to be redone. So that's one challenge. Another challenge is if you go to deep paleo, the critters that existed back then are different than the critters in the modern ocean. And so the whole formulation of the model may or may not really be appropriate for deep time paleo. I know very little about that, but I think that's a big challenge with if you try to do a sophisticated model in deep time paleo, then you've got challenges about your model representation just being inappropriate. The critters that we're representing might not have evolved a billion years ago, for instance.
Yeah. Thank you for this talk. I was just curious, you mentioned about the riverine inputs that are prescribed into the model. Is there any representation of human inputs of chemicals into the ocean?
Yes. Well, and we are using, when we have the prescribed riverine fluxes, those are over the historical period, and those do represent anthropogenic influence. So there is an increase, for instance, in nitrogen over the 20th century as fertilizer growth exploded. So yeah, so there is a representation in our data sets.
Okay, thank you. And just one other question. Is there any biogeochemistry in the lakes of the model or no?
I don't think so. You would need, I'm pretty sure the land, so that the lakes are, the modeling of lakes is done by the land model within CESM, and I'm pretty sure that, from my dabbling in the land model, it's just looking at heat content of lakes. I don't think they're considering biology there. I don't know that our open ocean representations would be appropriate to the organisms that reside in the lakes or the freshwater characteristics that live there.
I have two questions. First one is like, how about the resolution in biogeochemistry part? Is the same resolution as the ocean one, or if their resolution are different, how will they be coupled together?
They're the same.
They're the same. Okay. The second one is since there is a riverine prescript riverine input and there is no output, how to close the balance, mass balance for phosphorus for some prescript just for some elements from the riverine?
That's a great question.
Yeah.
And the way that we do that is I'm not finding it right away. Riverine inputs are prescribed. Notice in the next bullet, the stuff that's buried in sediments are lost from the system. And so what we do is we tune the burial to match the riverine inputs. So in a pre-industrial state. So in the pre-industrial configuration of the model, we have a tuning knob on there's a certain fraction of this flux, particle flux that hits the seafloor. A fraction of that is buried. There's a parameterization there. And there's a tuning knob on that. And we dial that in so that the stuff that's lost from the system balances that which is gained from the prescribed riverine fluxes.
So when projecting for the future, will this part be constant or dynamic?
The tuning parameter we then fix So you can get an imbalance if, for instance, the productivity declines in a future climate because of stratification, say, then you wouldn't get as much buried, and so you would get an imbalance. But I think that is something that you would expect that imbalance is realistic. That if you bury less, then there will be an imbalance. So that's how we try to that's what we do for that, achieve that balance. That's a good question.
Thank you.
Sure.
Yeah, we have time for one more question. Otherwise, can you stick a little bit
Sure.
around, because sometimes people prefer to ask the question in private.
Of course, yes.
Then, yeah, Keith will stay during the interruption. And yes, thanks again to Keith.
Yeah, we did that with CMIP. So CESM2, we did do CMIP experiments where there were carbon dioxide was being atmospheric carbon dioxide was being prognostically controlled by the model instead of prescribed.
So the forcing would be the emission, anthropogenic emission and
Exactly.
the internal variability of the carbon.
Yes, exactly. That's right.
Okay. So how long?
There's a long pre-industrial control run. I forget if it's 500 or 1,000 years, and then there's 20th century experiments as well.
We also do some cycle, but we use the.
Okay.
Maybe it's a very general question. I know there are many simple box model like. So do you know how do you think the pros and cons between?
It depends upon what you want to do. So, want to really capture spatial distributions, I think the simple models won't be able to represent that. Some of the projections might be a little questionable if simplifying assumptions in a simple model. For some stuff they can work well, but they have limitations.
Last question. So what's a tracer like for common system for tracer? It's a common tracer.
We have two. We have DIC and alkalinity. Yeah, exactly. Of course. Thank you for your questions. Hi.
Yeah. It is a good podcast. Okay, yeah. Okay, stop it immediately. Okay, hello. Okay, then we are going to start again. And the next presentation, it's from Ayla Simpson, that's going to talk about simpler model. Then you have CSM, but you have also possibility to run simpler model. I see Brain Dobbins.
Oh, a Brain. Yeah, it's appropriate. Yeah. All right. Can you hear me? Is this microphone working? Okay. Cool. So I'm going to give an overview of idealized modeling capabilities within CESM, and our ability to run these idealized configurations has grown a lot over the last year, and not last year, the last years, almost a decade now. And there's going to be more coming in the future. So as I think you all learned already, CSM consists of a number of different components, and they're all coupled together through the coupler. But even if you just take one of these components by itself, it's a pretty complicated thing to be looking at. So for example, if you take the atmosphere model, that consists of the atmospheric dynamical core. It's solving all the equations of motion on a grid on the sphere. I think you heard about that from Peter on Monday. And then that's coupled to a whole suite of physical parameterizations that are trying to represent these subgrid scale processes that are happening on too small of a scale for us to be simulating. And I think you also heard about that from a number of talks on Monday. And then if you're running atmosphere only, you still have to couple to the surface. So you'll couple to the land model, and you'll typically run with prescribed sea surface temperatures and sea ice. So even if you're just looking at the atmosphere, it's a very complicated model that you're looking at. And so typically what we'll do is we'll take CSM and we'll run an experiment through a very large supercomputer and come up with some representation of what we think the climate looks like. So for example, here's present day precipitation and then stationary waves as given by the sea level pressure in the CSM2 large ensemble. And then we'll run some perturbation, like run a future scenario and see how do these aspects of the climate system change. And so that's great. You can use CSM to come up with these kind of state-of-the-art projections of change. But the challenges really come in when you try and understand why has the model produced the changes that it has. And it can be difficult to truly understand what's going on just by looking at CESM itself. So what are the problems that we face when trying to gain that understanding? Well, one thing is that CSM is very complicated. There's many things going on, many processes, and they're all changing all at once. And the system tends to be in a balance. It's kind of always obeying the balances it's supposed to, like energy conservation, momentum conservation, moisture balances. And so what it means is that all the components are coupled. You change one thing and everything else starts to respond to try and maintain these balances. And that makes it very hard to kind of establish causality because you're normally already looking at it once everything has responded to give you a new kind of balanced state. And then, of course, we've had to use this massive supercomputer to come up with the answer, which kind of speaks to the complexity, right? You can't just think about how is the climate going to change, really, and come up with an answer, especially not for details. And so you needed to use a large supercomputer, which makes it difficult to interpret. So then how can we try and pull it all apart and try and understand what the model is doing? Well, you can get a long way with detailed diagnosis of model output, but you could also use simplified versions of CESM. Or you could perform idealized experiments with CESM with the comprehensive version of CSM, but simplify aspects of it. So really here I'm covering the simplified versions of CSM that we have available, although I will touch a bit on more idealized experiments with the comprehensive version of CESM. And so, as I mentioned, the capacity to run idealized models within CSM is growing. If you're interested in this, I'd encourage you to go to the Simpler Models webpage there, where you'll find lots of examples. Even if you're not interested in simpler models, you might find this a useful starting point for learning about source code modifications and things, because there are some simple examples in there. So simpler models, these are stripped down versions of CSM that either they only contain certain components or they have an idealized representation of certain components. And there are advantages and disadvantages to these idealized configurations. On the advantages side, they're typically easier to perturb, so you can change one thing and look at how the model responds, and that allows you to kind of get at causal pathways for how does one thing affect another thing, instead of just looking at this balanced system that's already responded. Typically, although not always, they're cheaper to run. Some of these you can run on your laptop. So if you're limited in your computational resources, there's more you can do with these idealized configurations. And because they're cheap to run and they're easy to perturb, you can do kind of parameter sweeps and look at a whole range of changes and be like, how does the system scale with whatever changes you've put in? On the con side, I'm just listing one, but it's a pretty major one, and that's that these models are, of course, less realistic. So I'd encourage you, if you're using these, always keep your eye on the real world or on the full version of CSM. I think these idealized configurations are best used when you're trying to explain something that you've seen in the full complicated system. So I'll run you through the atmospheric simpler models that we have available, and then I'll go on to the land and the ocean. The atmosphere is where most of the work has been done on this so far, but there are definitely some things coming down the pipeline very soon on the land and the ocean side. So here's a hierarchy of atmospheric components. Up on the top here, I'm not going to touch on these really, but these are idealized ways in which you can use the kind of full version of CAM. On the diagonal here, these are configurations where, oh, this pointer's so hard, where the full dynamics is there, but you have idealized representation of the physics. Down here in the bottom left, these are ones where you have some modification to the equations of motion that are being solved. And we don't have those. It doesn't really make sense to have those in a big Earth system model like CESM. And then the single column model off on its own has an idealized representation of the dynamics, which I'll get to in a minute. So this is what we have right now. And you can see that almost all of these configurations are now available within released versions of CESM. And I'll just run you through very quickly each of them to just give a brief explanation of what they are. So starting down here with the dry dynamical core, this is probably the simplest of our models that has the full dynamics. And basically what's done in this configuration is you take all of these physical parameterizations and you get rid of them and you replace them with a very simple Newtonian relaxation of the temperature field towards a specified temperature profile. So you've got rid of the radiation, clouds, and everything like that, and you're just representing them by relaxing the temperature to some chosen profile. And then there's a very simple linear drag on the winds at the lowest levels. As I go through these, I won't go in all the details of what's in these boxes. These are kind of on the slides for you to browse afterwards if you're interested. But I'll just kind of mention what these configurations are good for. So the dry dynamical core is good for dry dynamics. It's good for situations where you don't care about moisture or its interaction with the circulation. And there are examples where this is useful. For example, eddy mean flow interactions in the mid-latitude westerlies or stratosphere-troposphere coupling. That's actually where I started, is using one of these idealized models to look at that. And they're easy to perturb because you can change the temperature very easily. So for example, you could put in a warming in the high latitudes to mimic Arctic amplification and explore how does the jet stream respond to that. Those are the kind of things you can do with this idealized configuration. Moving on up the hierarchy, now we have the dynamical core with idealized moisture. And what's done here, if we take the dry dynamical core as a starting point, it's very similar to this more complex configuration. What we have now is a representation of moisture, but it's an idealized representation. So you have a water-covered Earth. Water can be evaporated from the surface. It's moved around by the circulation. It can reach saturation and condense and precipitate. and associated with that, you get a heating. So there is interaction between moisture and the circulation, but it's pretty idealized. And again, there's no radiation seeing this moisture, there's no clouds. And so this is good for situations where you care about how moisture is being transported, or you want to look at how does some heating associated with precipitation impact with the circulation. This is often used in dynamical core development, so you have a tracer here that you can look at how it's being moved around by the circulation. Our next complex configuration is the gray radiation aquaplanet. This is the most recent addition to the simpler models. And here, the way more complexity is introduced is instead of this relaxation of the temperature profile, you now have a radiation scheme. But it's a very simple radiation scheme. So you have one incoming shortwave band, and you have one long wave band, and you have one specified long wave absorber. So water vapor is not seen by the radiation. There's no clouds, but there is radiation there. And so this can be used for idealized studies where you want to kind of look at how does radiation interact with the circulation and with moisture, but it's in a very idealized setting, and it's very cheap to run. Moving on up now, we have radiative convective equilibrium world, and this is not that simple. This is using the full physics of CAM, but the simplification here is in the boundary conditions. And so what's done here is you have no land, you have no rotation, and you have no latitudinal variation in insolation. So you basically have a uniform planet, but you have all the physics, and this is kind of making the whole planet be kind of like the tropics. And so it's useful for looking at kind of the processes that are relevant for the tropics. And the example I'm showing here is from the description paper of this configuration, and it's a phenomena that's commonly studied with this, and that's the aggregation of convection. So what you see here is rain, precipitation, and outgoing long-wave radiation, and you see on the cooler planet, the convection is much less aggregated than in the warmer planet, where it's kind of more aggregated into these big structures. And where this can become really interesting is where you take many different models and you put them all in this same idealized footing. And you think, well, then maybe they're all going to respond the same because there's not that much complexity here, but they really don't. And that's when you can kind of start to understand how differences in the model physics are responding differently to perturbations across models. So now the aquaplanet here, this is our most complex, simpler model. And really the only simplification here is there's no land. So you have a water-covered Earth. You can have prescribed sea surface temperatures, or you can run with a slab ocean. Here you do have rotation, and you do have latitudinally varying insolation. So you have a pretty realistic planet from the perspective of most things. You just don't have land, and you don't have the asymmetries kind of in the longitudinal direction that come along with that. And an advantage of that is if you're looking at something where you don't really care about that, you can get much better statistics because the whole planet is kind of behaving in the same way around the longitudinal direction. Okay, over here to the single column model, this is kind of the opposite of those other configurations. Here, there's really no dynamics. You're prescribing the dynamics, and you're just solving for how do the physical processes behave in a single column. So you're basically taking CAM and you're taking one location on the planet, giving it time-varying atmospheric circulation, but looking at how the physical processes in that one column behave. So for example, here in this figure, this is showing cloud fraction. The bottom panel is from a CESM run, and then the top panel is in the single column model driven by that CESM run. And so the single column model can very well reproduce what was seen in the original configuration. And what you can do now is change parameters in the physics and look at how do these parameterizations change under that constraint of having the same circulation. So this is very commonly used in model development, but it can also be used to kind of gain fundamental understanding of the behavior of, say, convection in the tropics and things like that. Okay, now moving on to land simpler models, and we have a simpler model for the land coming soon. This is the Simple Land Interface Model, or SLIM. This was developed by Marisa Legou. She's now at the University of Utah. And the idea here is that CLM5 is very complicated, and sometimes you might want to perturb something in the land, say surface roughness or albedo, or the ability of the land to evaporate. And that's really difficult to do in CLM because those processes are kind of a result of what the model is producing. Those are prognostic quantities. So it's hard to just go and say, I want this albedo in CLM. But SLIM is a much simpler land model. It's kind of going back to the olden days of land modeling. You have a very simple kind of representation of the thermodynamics in the soil. You have a bucket where you kind of decide how deep you want your bucket to be, and that kind of determines how much water the land surface can hold. You can specify the roughness, you can specify the albedo, and you can specify the depth over which snow starts to cover the surface. So SLIM is much less complicated. If you're a carbon cycle person, SLIM is no use to you. But if you're wanting to look at how does changing something at the surface impact on the atmosphere, you can have a lot more control in using this simplified land model. And so don't look at my slides from last year because I had something very similar. It's been delayed a little. Last year I thought it was going to be ready at the end of the summer, but our software engineers are always have many things going on. But we really are trying to get this available early next year. And if you want to use it now, you can get in touch with me, and I can tell you how you can get to using it now. So I just want to finish up with a quick word about coupled idealized modeling, because we have some new tools coming down the pipeline to do that. And so this is a project that's involved many people. And what we're aiming to do with these tools is make it easier for you to decide how to set up idealized configurations where you maybe want to just change the shape of the continents or change the land surface properties or change the orography and things like that. And I'm just going to run through a quick example of what this tool is going to be capable of with this example of the ridge world. This is a coupled aquaplanet where you have a full dynamic ocean, but you have a ridge of land, and then you have some polar land caps. And to set this up in CSM is not trivial. You need many different files to change the land mass, change the land surface properties, and change the bathymetry and things like that. So I have a very quick movie, which is going to run away from me because it's going to go faster than I can talk, but I will try and run you through it. So it's a Jupyter-based GUI. And what you can do is it can guide you through the whole process. And this can work for just setting up regular CESM cases. It's already going too fast. So basically what you do is that you can set up, choose the different components that you want to have in your model. And you'll see that as you choose them, it will kind of cross out ones that are not compatible. So here you choose CAM, and it crosses out ones that aren't compatible. So you choose all your different components. And then within each component, you can make a choice of what kind of physics do you want. And some of them don't have choices. And then you can also choose some kind of like specialized modifiers. For example, here I chose satellite phenology in the land. And now this is where we're setting up our custom grid, and this is where this tool becomes really useful. So here I'm just giving it a directory where it's going to put the new grid. And then in the next step, we're just selecting the atmosphere grid. There's not much choice there. But now we're going to set up our kind of user-defined ocean grid. And what I'm going to do here is going to make it have a 1 degree grid. And then when you click on this green button, that's going to take you to this bathymetry tool, which will help you guide you through the setup of your own bathymetry and your own land surface properties. And that is not something that's kind of easy to do outside of this tool. And when we get to this tool, I'm just going to give it kind of there are various ways you can change the bathymetry. You can point and click, or you can give it a file. I'm just going to copy in a kind of analytical profile for the bathymetry from another notebook. And you'll see that I can then plot the bathymetry and make sure it's looking good. Here, it's already imported the details of the ocean grid from the previous notebook. And then here's where I'm configuring the ocean bathymetry. And along with that comes the land sea mask. Here, I'm just copying my user-defined bathymetry. And I'll go and paste that into this notebook. And then in the next cell, I'm just going to plot the bathymetry, make sure it looks good. And then in the last cell, so this is our ridge world bathymetry, then it's outputting all of these input files that are needed for the land model. And then once you've done that, you can go back to the original GUI and go through the same kind of thing for the land. So this is coming soon. If you're interested in trying out, please do so. There's going to be problems, but please get in touch when you find problems, because that's what we want to hear about. Okay, so to conclude, we have various simpler models that within CSM, these can be useful if you don't have a lot of computing time or if you want to try and gain some understanding of the system. They're pretty well documented. I'd encourage you to go and check out these websites. The mailing list one here is out of date. I will try and update this for the website, but the other two work. So thanks for your time, and I'll take any questions.
Question for Ayla?
Hi, thank you for the talk. That was really interesting. So you mentioned a lot of like more idealized versions of CAM and the land model. And from what I've been hearing from a couple other NCAR scientists, the ocean model POP is being replaced with MOM6. So are there simpler models of POP or MOM6 that can be run? Like what sorts of models are there? And then part two of that question is kind of like, is there an idealized coupled model that can be run, like an idealized atmosphere ocean model? Can we only can we use an idealized component from two different parts of CESM and run them together?
Yes. Okay. So yeah, there are various parts to that question. So on the ocean side, I think that we will have a lot more capability for idealized modeling with MOM. I believe they can run that in a kind of channel mode, and it doesn't have to be a global model. So I think there will be lots more coming once that is released, and hopefully we can incorporate that into future tutorials. There are existing simpler ocean models. I should have added one of them is available. That's the slab ocean, where you basically prescribe a mixed layer depth and you just have a thermodynamic slab. I do have an extra slide here for another one, which is not available yet, but it's hopefully coming soon. And that's this pencil model. So the slab is basically the one on the right there, sorry, the second from the right. And the full dynamic ocean would be the one on the left. And the pencil model is somewhere in between. You're basically running a single column ocean model at each grid point. So there's no large scale ocean circulation, but you do have the kind of vertical mixing processes and things. And the advantage of that over the slab is that you don't have to pre-prescribe mixed layer depth. The model is calculating that, and it's calculating the kind of fluxes associated with vertical mixing. Young-Oh Kwan and his group are developing this, and I think they're pretty close to running along pre-industrial control. So I think this is hopefully going to be available for use kind of in the next year or so, but there are various hiccups that have happened along the way, and there may be more of those. In terms of running idealized multiple components, for many of those atmospheric components, they're too idealized to really couple to the land. You need to have the full radiation scheme for that. But you could certainly run like RCE World with an idealized patch of land, or the Aquaplanet with idealized patches of land. And you can run like the aquaplanet with a slab ocean, for example. So there definitely are combinations that work. But there are also combinations that don't work. For example, the dry dynamical core, you can't couple that to anything because there's no radiative fluxes that those other models need.
Thank you. I also wanted to ask, so here we see like multiple choices for like an ocean model when coupled with the atmosphere. I, I guess like is there the opposite version? Like could you run like a pretty solid ocean model but have a super idealized atmosphere with it?
That would be great. I would love it if we had some kind of like boundary layer model that we could couple to the ocean and the land. We don't have that capability right now. There's definitely scope for users to contribute things, like if someone was to develop that capability within CESM and it becomes very popular, then we would definitely add something like that into these configurations, but we don't have that right now.
Hi, thank you. I have a question about the single column atmospheric model. So would it be possible to add the chemistry module in the scheme? Since it seems that there is no large-scale transportation, so I'm curious about whether this model can simulate the concentration of air pollutants in a specific location.
So the first part was about CAM3, or?
Yes, would it possible to add the chemistry model in the scheme, just like the CAM? If it's possible to use the scheme CAM, this kind of, yeah.
Oh, so you want to have with coupled chemistry, you want to have the single column model with coupled chemistry, is that?
Yeah.
Cecile, do you know, can we do that? I think we can, but I'm not sure.
We have the chemist here tomorrow, then maybe it would be a good question for them. Rebecca would be here tomorrow.
Yeah, because I found that we can add the name list, the chemistry scheme in the name list.
Okay, and did it work, or it didn't work?
But the simulation of the air pollution seems not so well. So yeah.
I think there can be problems if you don't, like, things can run away from in SCAM because suppose you change something and you're constantly bringing in some quantity of something. It can kind of accumulate if the system isn't really able to respond and move it out. So there are features of SCAM where you kind of often, for like aerosols, you relax towards some climatology to prevent that drift towards unrealistic states, and it could be that you need to have that, or that was messing up with what you were trying to see.
Okay, thank you.
But maybe the chemists will have a better idea tomorrow.
Okay, thank you.
Another question? I think we have time for one quick question. Otherwise, I will ask Ayla, can you stick a little bit longer? We are going just to have a very brief overview.
Yep.
Check in, and after, if people have questions, sometimes they prefer to ask in private.
Yep.
Okay. Thank you so much. Thanks again, Ayla.
Oh, should have.
A quick in before we. I have the slide here, but it's not showing. Sorry? Oh, the mic is off. Yeah. Everything is off. The mic is off, my slide is off, but I have the slide showing here, and I don't know why it doesn't show. Maybe we should go home. Yeah, this is this one, yeah. It's the one we just download together. But, oh, okay. Okay, perfect. Thank you. Thank you so much. No, we're not going home yet. Oh, but I don't have anything to move the slide. I don't see the slide here. Either they are there, or maybe I can move it with this. There are no slides here now. Maybe we are going home. This is so funny. Maybe I broke the whole thing. Can I move it with this? Maybe just. Okay, let's try. Let's try to move it with this, and if it works. Oh. Whoop. Oh no. Oh, okay. Thank you. Thank you. Okay. We are not going home. Yeah. Wait. Okay. I can never overspend. I'm going to tell you we have absolutely no idea what's going on. We had twice as much resources as previous year. We saw maybe it's an issue with building in the tutorial queue. It's not something that we were doing in previous year, but Brian Dobbin checked and he doesn't think it's the issue. I think the only explanation is that last year we had clueless students that were not able to do the exercise, and this year we have very efficient students, and you did all the exercise and you burn all the resources. It's the only explanation. But let's save up the leftover resources. Let's not run the 4-year, because it seems if everybody succeeds to run it, it's too expensive, and I'm afraid we will end up in the same situation tomorrow. Then if you didn't complete the 4-year simulation, hold off. We will share the result with the people who didn't complete this simulation. And if you run it, it's great, but let's not run it otherwise. Let's see if it works. Okay. If you get this error, I get somebody who got this error. I don't see where you are. Yeah. It was we could not understand because yesterday he was in the tutorial queue, and then this morning he was not in the tutorial queue. And I talked to Rory, and Rory has to create a reservation for every day, and he has to put you in every reservation. Then even if you are in the tutorial queue one day, doesn't mean that you are in the tutorial queue the next day. Then it can happen, and I think George had the same problem the day before. Then if you see this error, PBS cannot successful start job, call me and we will contact directly Rory, and hopefully we can have you set quickly. But this seems that we understand now this error. Last thing, I had somebody that asked me, yeah, she's there, I don't know your name. I found it was a very good question. She said that it's very confusing. We talk about output, we talk about history file, and we talk about archive. And what is what? It's very confusing, and especially that sometimes we start to use the same word to talk about different things. Then we say output file, and sometimes it means history file, and sometimes it means some kind of other output. Then I put this quickly just during Keith's talk. Then it's not perfect, but this is, I can explain more, but I want to try to give you a little bit a definition of the different thing. Then this is here all the directory of CSM. Then basically you have, okay, this thing doesn't like me. Okay. Sorry, okay. Then in the green, you have the code, the model code. It's in your home directory, in a directory that's called code, my CSM code or something like this. Then after, when you do create new case, and in this you have, if you look here, how did you make this work, Ayla? Oh, sorry? Yeah. Okay, I think we should really go. Okay, then I'm going to, not to touch the screen, don't worry, but I'm going to point with my line. If you look here in this green code, you have something that's called create new case. It's the script that you are using to create a new case. You have done a few now. Then this is located there. When you do this, when you do a create new case, it's going to create this case directory, which is in your home directory under something that's called cases, and then the name of your case. And then there you have the 3 following scripts: case setup, case build, and case submit. This is one thing. Then when you are going to set up, build, QCMD, -Q tutorial, blah, 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 and then you do case submit, what's going to happen? It's going to create a bunch of files into what we call the run directory. The run directory, it's located inside this orange file, and it's like glade, derecho, scratch, your username, and the case name run. Then this is where you are. And if you look while it's running, you will see file appearing. You will have files that are called H0, files that are called log. There will be a lot of files that are going to be created there. And at the end, it's moved to another, when the run complete, it's moved to another directory that's called the archive directory. And if you look inside this archive directory, you have a lot of subdirectory. It's the stuff in blue, ATM, for the atmosphere, the land, etc. Then all the files that are created in the orange directory are moved at the end of the run in the blue directory. Then now, the history file, it's the file that are H0, and then today you will create H1, H2. Why is it called history file? We had a long discussion at lunch. It's a question for Peter Jens that were here this morning. I have been here for 20 years, and we have been calling this history file, and I don't know really the reason why it's called history file and not output file, but this is called history file. It is H0 file. But sometimes some of us call this output file, but it's the same as history file. Sometimes we call output file history file. It's this H0. It's the file you create in the model, and it's the file you want to look at. Now, when we call the output, it's all the files that are coming out of the model when you are running. It includes all this history file, but it creates also a bunch of other files: initial file, log file, timing file, error pointer, restart file. There are a lot of other files. And sometimes when you say the output, it's all of this. But sometimes when you say the output, it's the history file. And I'm sorry, I look at the documentation, and I agree, it's really confusing. It's our jargon. Then I have talked, and we want to create a glossary at the end, and people can try to figure out. And then the last thing, the archive, it's this directory in blue where the history file and the log file and are going at the end of the run. Does it clarify a little bit? It's there, and then you can go into the case you create and try to figure out if you understand what's going on. And so otherwise, call us. This is not, it's a lot of information that you are getting in 1 week. And we have been using this jargon for, in my case, 20 years, but sometimes don't be afraid to say what's history file, what's output file, what's archive. And again, I create this slide, and they will put it into on the website, I hope the link will go more quickly. We had one person that were putting the link. She was very efficient, but then another person was not as efficient. It was why it was not created, but I will try that this goes very quickly. I will check with them. Okay? Then we can go back to the lab now. There should be snack in the diamond room, not like this morning when I say they are reimbursing us for the bagel you didn't have, but